I've lost the ability to, oh, there we go. Hi, welcome everyone to the International Astronomy Day 2021. We're just getting started here this evening with a little smorgasbord of a few different things. We'll have some solar observing, a few glimpses of our virtual tour of the center and the telescope, as well as some historical photos of the observatory and its construction. We'll be off and on that until about 8 o'clock when our full program starts. If you have any questions while we're going this hour, either specifically about what we're looking at or any questions you might have for our Ask an Astronomer panel later on this evening, please don't hesitate to put them into the Q&A box at the on the webinar. Should be a link on your screen or somewhere on your Zoom application. I think we'll get started here with some solar observing. Our folks out in the parking lot have just caught the sun in their telescope and got it all sorted out through their software. So we'll pass it over to David.
Welcome to International Astronomy Day. And I think we have the sun. So we saw a couple of prominences yesterday. They were down around this region, but there's one here today, right in this area here.
David, can you tell us what we're looking at? What's the screen showing?
Just a second. I kind of lost the signal here. We're seeing the sun through a solar telescope, a hydrogen alpha telescope, and you can actually see prominences in this region here. So these are elevations from the surface of the sun. And if I switch the exposure, we should be able to see some granulation. There we go. So we see a sunspot here. And these whorls here is what we call granulation.
Okay, let's go back a bit. Where are you right now?
I am out on the parking lot right now.
Parking lot at the observatory,
yep,
up on Little Saanich Mountain. And you have a special telescope. What makes it special?
It's specially filtered so that it only lets through a very narrow wavelength of light associated with hydrogen alpha.
And
did
why
you want to see the scope? Or
it'd be great to see the scope.
Okay, let's see if we can try and do this. Hold on. Okay, if you can spotlight me, I don't know if that's working.
Yep, you're spotlit.
So here we have the telescope. So this is a brand new Coronado 90 millimeter telescope.
It's a double stack.
And so this is a special telescope that has filters on the far end and here in the diagonal. And this only allows a very narrow wavelength of red light through into the telescope. And that is associated with the alpha emission line of hydrogen. So a lot of the sun is hydrogen. So when hydrogen is reacting, it is releasing energy, and one of those visible wavelengths is in the red band. This is the camera. Hopefully you can see that.
Yep, we see that.
And it's connected. David Lee is over here. I'll just show you. And in this box is his laptop, where we're trying to see this because it's very hard to see laptops up on this hill at the moment. But so bear with us.
So Chris, James DeFrancesco wants to have a public service announcement about not looking at the sun. What can you tell us about that?
Yes. So as probably you're aware, if you've ever tried to look at the sun, your body doesn't let you, and that's because it's so bright it's actually dangerous. And so it's a normal reflex. Our eyes don't let us do it. But sometimes if you were to look in the direction of the sun with a telescope or binoculars, you could accidentally see it. And that would could cause a lot of damage to your eyes. So unless you have proper equipment, you should never use anything that's magnifying near the sun. So this telescope has proper filters on it. You can also get a different type of filter, which allows all the wavelengths through, but filters it down so it's only about 1/10,000th of the light gets through. And then that makes the telescope safe. But otherwise, don't do it.
Mm-hmm.
Thank
All
you.
right. Why don't we pop back over to the images coming through, and you can tell us a little bit more about what we're seeing in there. Okay.
So, all right, hopefully that's up on the screen there, and you'll see that it is kind of a reddy orange color. And that's because that's the wavelength of the light that's coming through. And when you look at the sun, you can see surface details or details around the perimeter. And which one do we have this set to, David? What do we have it set to? Prominence or
Granulation.
Granulation, yeah.
Yeah, so what are those granules there? What are they actually physically?
Oh, these are the gas coming out from the center of the sun, boiling up and cooling, going down again. These are little tornadoes.
And how big are those? Like, what's the size of one of these granules we're seeing?
Oh, could be the size of our Earth quite easily.
Bella, who's 10 years old, asks, what causes the sunspots?
Those are the magnetic field concentration and cooling the atmosphere of the sun, so it looks dark, but there is still quite warm, quite hot, shall we say.
Yeah, so one thing I heard or read about was if you think of the sun as being something like a boiling pot, every now and then you can get an area due to magnetic forces where the material doesn't get to the surface. And so it's about 1,000 degrees Celsius cooler, and it shows up as a dark spot.
So if you covered the bright surface of the sun and look at the dark spots, they look bright instead of dark.
Mm-hmm.
If I could interject here a few seconds, I would like to show this view to my dear friend, Roy Watson. If he's watching here, this is for him. He's a longtime member, dedicated volunteer for public outreach events. I'm pretty sure they wish he could come and set up his telescope here.
Thank you, Sid. So I wanted to ask a clarifying question here. So you mentioned granulations and sunspots. Are those the same thing here, or are we seeing two different things?
Sunspots is different than granulation. Sunspots, normally sun cycle is 11-year cycle. Sometimes we don't see any sunspot. And luckily for us today, we got a beautiful big sunspot there. And we were looking at it a couple of weeks ago. It was towards the east side, is going towards the west. Now it's going to disappear within a couple of days. So this is the way we are able to find the rotational cycle of the sun by monitoring the sunspots easily.
How long does it take?
Sun takes about 25 days to make one rotation.
Okay. We have a question.
Yeah.
We have a question
Before you
from,
go, if you close the equator, it's going faster than towards the poles.
right, because the sun doesn't have a solid surface. The
No, that's
equator
right.
spins around faster. The poles are sort of sitting still.
Yeah.
We have a question from River over on the YouTube. She asks, why is the sun hot?
Oh, very interesting aspect. I'm so glad sun is hot. Otherwise, we will be freezing cold here on the Earth here, because there is a nuclear, not explosions taking place in the center of the sun. Is the thermal nuclear, is a hydrogen actually, because the temperature is so hot and high pressure, the hydrogen molecules or atoms are combining to turn into helium. And so as the combination from helium, hydrogen to helium, it releases a lot of energy. And eventually, after thousands or hundreds of years, it comes out to the surface, and we are able to admire this nice sun surface.
All right. And I should mention this question asker is 4 years old. So can you give us a simpler version of the explanation as well? For those who may not have a background
like
of nuclear science.
Yeah, we got fuel, hydrogen. If you burn, it's like if your fireplace. So
Yeah.
Fireplace, you start burning all the wood or the charcoals, and eventually it heats up, and high temperature turns into white hot, and it releases its heat eventually.
Yeah.
And one of the other things maybe we could mention too is that was said when I was showing you the telescope that we focus on this one particular wavelength of red light. So apart from all the heat, there's visible light coming out of this reaction. There's also other wavelengths of energy, such as X-rays and many other things. And that's one of the reasons why it's difficult to get a probe closer to the sun, because it's very inhospitable. So there are new efforts made to get something closer to the sun, but we haven't been actually all that close to it yet, because it's so so dangerous there, and it's so inhospitable, I guess is the best thing to say. It's so hot and dangerous wavelengths and various other things happening. So
excellent, thank you.
There's a question. Pat's 6-year-old daughter would like to know what a solar prominence is. So David, can you change the exposure so we can see the outside of the sun? And can somebody help Pat's daughter know what a prominence is? First of all, where do you see a prominence?
Yeah, where David's arrow is.
So it's around the kind of 2 o'clock position, if you think of it as a face of a clock. So what's happening is, if this is the sun is a ball of gas, and getting back to that boiling pot idea, stuff is coming up to the surface, and it often keeps going. So you get hydrogen going beyond the disk here, and as it was also mentioned, there's quite a lot of magnetism on the in the sun, and so you can find lines of hydrogen going beyond the disk and forming so you get a band of hydrogen kind of outside in space, if you were. And it's a little bit hard to see there, but where David's pointing out, and we've magnified it, that is some hydrogen that is out beyond the disk, if you like.
And that's probably about the size of the Earth there, isn't it?
Easily, yeah, probably more like 3 or 4.
Oh boy.
The Earth fits across the diameter of the sun over 100 times, and that looks like it would be well over 100th of the the diameter of the sun. So yes, that is huge.
If you look, David's cursor is probably a rice size Earth.
Uh-huh. Now, I'd like to know, what is the relationship between that and the Northern Lights, the aurora?
If there is a, what they call it, the sun explosion on the surface, and it throws flares. And when the flares reach our Earth magnetic field, and where the north and south pole of the Earth, you see this. After a couple of days of when the flare takes place, you will see northern lights or southern lights.
If I can add, there's a constant wind of charged particles flowing off of the sun towards the Earth, and it's there all the time. And it gets stronger when there's lots of sunspots. So when there are lots of sunspots and lots of prominences, that increases the flow into the solar wind and causes very dramatic aurora borealis and aurora australis in the southern hemisphere.
Go back out again and see if we can. We're just going to go back out again and see if we can see. There was questions, are there any other prominences today? And there might have been one on, well, there should be prominences in theory all the way around the sun. But as we mentioned, that for us to see them with this type of telescope, they have to be really large. So maybe if, could we look just on the, I guess the eastern side there at 9 o'clock position, David? Can we try zooming in there and just see if there's anything over there? But again, they may not be big enough to see.
Well, there are some prominences.
And then you see them in profile also.
Yeah.
You can see them from the side, but if they're on the disk of the sun, they don't stand out.
No.
Don Moffat points out that some of these storms are big enough that it affects our hydroelectric wires, and you can get voltage surges of 1,000 volts in the wires. And I remember there's one time that a lot of the Quebec power system went out because of one of these storms.
Look at the prominences where David's cursor is.
Oh yeah, there's another.
Yeah. We are lucky today because we got prominences, we got sunspots. Sometimes so bland to look at the surface of the Earth, of the sun. There's nothing to show. It's a good show today.
Chris, that prominence looks like it's actually breaking up a little bit.
Yes, it could well be.
Doesn't it?
And that is on the leading edge of the sun. It rotates that way because we should also let you know you're seeing the sun reverse. So this is actually the if you were to be able to look at the sun, this is actually the right side of the sun, not the left. But it gets reversed through the telescope. And it could be that it's rotating away from us too. So it may be just passing the bulge, as it were, and vanishing from view. And they do also degenerate after time too, but because they're so large and a lot of the time form around magnetic lines of force, they do tend to be there for quite a long time.
More questions?
Actually, this prominence was around yesterday, actually.
Yeah.
And often they form a loop, but we don't see it today because it could be turning away.
Okay. All right. Are there any other features we should take a look at, or?
Ooh, that looks
Oh,
good.
this is good. Look at that.
Yeah.
David, scan around the edge now that we see
Beauty.
it so nicely.
Yeah.
Oh, lovely.
Okay, so we've had a question of how long ago have these occurred. So the sun is about 8 minutes away from the Earth, 8 light minutes away from the Earth. So it's a little over, you're seeing the sun as it was a little over 8 minutes ago.
Bill asks, hi guys, I'm curious. You guys are outside and don't seem to have anybody near you. Oh, so why the masks? I know you're both handsome men. So the folks out in the parking lot, I believe, are all fairly close to each other, but they all have their computers pointing in different directions.
There, I've just turned my camera around a bit, and you can see I'm sitting beside David, so I'm within 2 meters of David. So,
But they're sitting so close to each other. Yeah.
yeah, we're at a 2 meter long table, so we are at opposite ends, but we are close together.
Did I see something at the North Pole there, David?
No, there should be
12
nothing.
o'clock?
There's one here. There's almost a floating spot, and then this one here.
Can you go back up to the North Pole?
Just forward you a message from Kim. She's fine. She just.
Oh, Bella has another question. Are there hundreds of sunspots or just one or two? Or does it depend on the strength of the telescope or the filters color that are used? Excellent questions.
Yeah, so basically, yeah, a lot of that would be true. So first of all, as Sid mentioned, there's a cycle, and we've just coming off a minimum. So there hadn't been very many sunspots, at least ones that we could see from Earth. But as you remember, they have to be quite large for us to see them. So I would expect there are probably some smaller ones that could be there, but they're just not big enough for us to detect. So there's a bit of that too, but we should be going into a time where there are more and more sunspots for about the next 5 years or so.
Oh, look at
And I'll just let folks know, we do have, because this is a webinar, we do have a cool Q&A feature. There should be a button on your, if you tap your screen, if you're on mobile, or you can pull it up from the More Options menu. That way we can keep track of all the questions and filter them out from the chat. That's the best way to ask a question for us. So you can make sure we get to everyone and they don't disappear on us.
Thanks, David.
So I have a question. Why is the picture shaking around like that or wobbling?
That is a good question. So one of the things is that the sun is getting lower in the sky. So we're actually looking through more and more atmosphere. So that's one of the issues with looking at things from the Earth, is you're always looking through a lot of massive moving air. And the lower down something gets, so that you're looking closer to the horizon, the more it tends to dance. So.
We have a couple more questions. Anthony asks, there was a reference to the sun's North Pole. Does the sun have a magnetic North Pole?
Well, it has a center of rotation, if you like. So when you look at the sun, it does rotate or somewhat around an axis, but it's not a magnetic North Pole as such. The sun tends to have strands of magnetic force that are that can appear anywhere. And because it's gas, this is why they can form together and clump and form these sunspots, because you can get a kind of tangled knot of magnetic force lines that stops the flow of heat to the surface over a smaller area, and then you get that slightly cooler area at the surface. But the sun does rotate around an axis, so that's when we talk about it having a north pole, that's more what we're referring to.
Well, everybody, this has been great. I think we're going to take a pause on the sun and hopefully get back to it before the end of this hour. But now I'd like to ask Calvin to take us up to the big telescope.
Hey, everybody. My name is Calvin. Yes, I can do a bit of a virtual tour of the Dominion Astrophysical Observatory. You may have seen a bit of it in the background there for David Lee and Chris Peirce. So I'm going to share my screen and make sure I have it all ready here. I do want to ask, I want to see if how many people have actually been to the Dominion Astrophysical Observatory in Victoria, BC. People want to just throw in chat a yes or a no. But this is a hill on near Victoria, BC, and actually Saanich. And I'm going to scroll around, and you can see the Dominion Astrophysical Observatory. This is the big white building with a dome on top. And we can go in and take a look. There's also this image here. I think it will show up. It might be a little bit small, but this kind of shows an older photo of the dome when it was much more new. But let's go inside and take a look. So here's the inside of the dome. On the floor here, it says DAO, which stands for Dominion Astrophysical Observatory, and the year that the building was built. That's 1916. So this building is over 100 years old. And somewhere in here is a telescope, but we don't see one just yet. Here is what's called the pier. This is a bunch of cement that acts as the foundation for the telescope to keep it very stable so it doesn't shake or wobble. It goes several, I think a couple stories down the ground as a good foundation should do. And the telescope sits on top of it, somewhere up here beyond the ceiling. So we have to actually go to the second floor to take a look. All right, so here is the Plaskett Telescope. This blue part here is more of that foundation that I talked about, the pier. And then this yellow part is the axle or the mount. And this is what lets the telescope rotate around. You can see big gears here attached to a electric motor that rotates the telescope around. This is the most important part of the telescope. This is the telescope here, this big long tube that's black and white. And so there's also the ceiling, of course, the dome that holds everything, covers everything up. There's a shutter here that can open up because it would be quite unimpressive if this telescope couldn't actually look outside. Also, it would also be boring if the telescope could only look directly upward. So like I said, the telescope can rotate around, but also this opening here can look around as well, can move around as well. There are wheels between this green and white part here. You can see wheels. These are on tracks, just like train tracks. So these can rotate around, and so the opening can point in another direction.
So Calvin, this tour, anybody can do online, right?
Yes. This
Can
tour,
somebody put into the chat the address of this, because this is really cool.
yeah, that would be a good thing to do. Maybe I can do it quickly. I think we can get somebody else on it. So yes, this is our virtual tour, which is just on our website, centeroftheuniverse.org. So anyone can take a look around. I can also do a bit of an explanation as to how a telescope works. This is kind of nice to see here. Okay, because the most important part of the telescope is the mirror, which is the thing that takes a dim object and makes it look brighter. So at the bottom here is a very large mirror. It's 1.8 meters in diameter. So it collects all of that light and then it reflects and focuses down to a secondary mirror, which is up here, and then reflects and focuses again. So it goes down to a point through a hole in the main mirror down to this device here. And in here is a camera that collects all that light and takes a picture so that it makes a picture of a star. In this case, this particular device is a spectrograph. So it doesn't just look at the picture of the star as we normally take a picture of it. It actually spreads the light out into a rainbow. And that way we can figure out what color it is, which might sound kind of boring at first, but color is incredibly important in figuring out what stars are made out of.
Calvin, there's a couple of questions. What type of telescope is it?
What type of telescope? This is, I'm pretty sure, a Cassegrain is what it is called, or I might be forgetting, it might be a Schmidt-Cassegrain. I think it's a Cassegrain. So that style is that you have a hole in the mirror, and that's your either an eyepiece or a camera goes at the bottom. Other mounts have like I think the Newtonian style actually has an eyepiece around here. And in fact, this telescope can do that as well. You can have a different secondary mirror so that after the light gets collected by the big mirror and reflected up to the secondary mirror, it can actually point in this direction out the side. And so there's a different kind of camera in there as well. So this particular telescope, the Plaskett Telescope, you can kind of swap out those two depending on the kind of observing you want to do.
And is the telescope still in use? If so, who uses it and what are they studying?
Excellent question. Yes. This telescope is over 100 years old. As I said, the building is over 100 years old. So this telescope is as well. And yet it is still used. Like every night that it's clear out, this telescope gets used for science. I know that it does get used for all kinds of different kinds of observing. Astronomers usually book time for their own projects on here. I know a very, very common one is to search for near-Earth objects, so asteroids that cross or get near Earth's orbital path. And so there's an astronomer that is always looking for them and finding hundreds over, I think, decades with this particular telescope. I can show you the control room. It basically looks like a office. It's quite straightforward, but this is where the astronomer would work. They'd stay up all night. From this computer, they can operate everything. They can turn the telescope, they can move the dome around, open the shutters, and also, of course, take pictures of the stars. And so that's where they would work. I do know that it has been modified so that can also be run remotely as well.
Calvin, it will be run remotely tonight, right when we're finished at 11 o'clock. Then somebody will be right on and right starting as the weather still is really good. Oh.
Awesome. Yeah, that sounds great. So there you go. It's continuing to operate. So I did mention that this telescope can rotate around a point in different directions. This is just a static image, but we do have a video. We did capture a video of it operational so that we can actually show people. So Aaron, are you there? And do you have that
Yes,
ready?
I can. And I'll just remind folks, if you have a question, please post it in the question and answer box rather than the Zoom chat. That way we can make sure we get to it and it doesn't scroll up in the chat window. Let's see. I'll bring up our video here.
Okay, I'll stop sharing that.
And if we don't get to your question now, we will try and get to it during our Q&A session, or Ask an Astronomer session later on. If your question is dismissed, that means that we've saved it for the Ask an Astronomer specifically, because we want to get to it. Okay.
Well, somebody's getting ready. Oh, you're ready now? Good.
Yeah.
So.
Oh, and I don't think we're getting the sound through here, but that's okay. Let's see. Okay. Yeah. So first off, the dome opens up the shutter. It's like a set of two big elevator doors sliding out side to side, and then the that canvas at the top slides off, which protects the telescope from any like sticks or anything that are on top that could fall down into it. The whole dome can turn around 360 degrees. There's a close-up of the wheels there. So they are actually railroad wheels. The dome was built by a railway company from Chicago. And it can go all 360 degrees. It can go around multiple times if it needs to. Let's see. Oh, Kevin asks, are there filters or spectrums of light that can be seen through the clouds, or can it not be used at all when there are clouds? There are spectrums of light that can see through the clouds, but they can't be seen by this telescope. Different types of telescopes, like radio telescopes, can see through the clouds, but not a visible light telescope like ours. So once the dome is positioned right, then the telescope can move. So it turns around that polar axis in the middle there, and can also turn using the on an axis through the counterweight there. Now that's much, much faster than the telescope can actually go. This video is sped up a fair bit. This is not the Ferrari of telescopes, but all of the motors and mechanics of, sorry, not the motors, but all the gears and internals of the telescope are still original. The motors, though, have been replaced, and the control systems. All right, back over to you, Calvin.
Okay, there's a great question from Maureen. Can anybody book a time? Is there a cost to booking time?
Interesting. I'm not too sure. I think for astronomers that want to book it.
Calvin?
Oh, yeah.
Yeah, if like every other telescope used by professional astronomers, there's a competition for time on the telescope. People submit proposals, and then they get reviewed by a committee who decide who gets the time. Nowadays, a lot of the observations, partly because of COVID and partly because of expense, are done by local professionals. So the people who want time on the telescope ask local people who are very experienced to actually do the observations for them. But some do come here to observe as well.
But it's not something that anybody can just say, here's a stack of money, I want to play with your telescope.
No. You can do that on SLU though, can't you?
That would be something.
I don't think there are any 1.8 meter telescopes in public use.
That'd be quite the project.
No, although this telescope has been continuously used for public outreach ever since it was first put online in 1918. It was a passion of the original director of the observatory, John Stanley Plaskett, to support public outreach. And he made the telescope available to people right from day one. And apart from COVID and 1 year during the Second World War, we've had star parties with people coming up on the hill to look at the telescope and the images from the telescope every year.
Yeah, so we've got a legacy of public observing here. I just wanted to pass along go through a couple of questions here. We've got a whole bunch in our Q&A box. This is great. Let's see. Peter Scott suggests reciprocal arrangements with antipodal or observatories on the other side of the world for remote control, so you can work all during the day instead of at night.
Can never sleep.
Yeah, well, astronomers do tend to be night owls. That tends to be part of why they get into the profession. But as well, a lot of telescopes nowadays are switching over to robotic control. So you don't actually have to stay up all night. You set up your observing plan, and then the telescope does it based on weather or other factors, or it's controlled from, such as in Hawaii, a ground station that's much closer to where people live and not way up on the top of the mountain. So they can monitor it closer to home.
And another point is that whenever something really new and interesting happens, like if a star were to explode close by, all the telescopes in the world collaborate on observing it 24/7. The most recent really bright exploding star near us was in 1987, discovered by a Canadian in Toronto, actually, working in Chile, if I remember correctly. And so as soon as that was noticed, all the telescopes around the world would swing into action to keep monitoring it all the time. The Hubble Space Telescope, which of course didn't exist at that time, is also quite often used for what they call targets of opportunity. So some new thing, like a burst in space that is not very well understood, that will get everyone's attention and all of the time.
Mm-hmm. Let's see. A question from YouTube: are the mirrors the original ones? So the telescope did have its original mirrors for quite a long time, but they were replaced, I believe, in the 70s with some ceramic ones instead of glass. But since then, they've been the same ones. Ria from YouTube asks, how often does the telescope need maintenance and how long does it take? And as far as I know, they have to recoat the mirror with a new layer of aluminum to do the reflecting every few, I think, 5 to 8 years. Sorry? 2 years. Well, they've been pushing it off for a little bit then. Yes. It can get away with a bit longer, but it does start to lose some reflectivity as it goes along. And they're working on revamping the system for doing that, because we still have the original re-illuminizing tank that recoats the mirror, but there's not many people who know how to use it anymore. So they're trying to train a new generation of engineers on how to recoat the mirror before that knowledge is lost.
Are we going to show the original mirror? Aaron is actually sitting staring at the original mirror for the telescope.
Oh yes, I can bring it up here.
So he can either turn around or it's on the tour.
I'll bring it around. And then, yeah, and again, for questions, we probably won't be able to get to all of them right now. But Nathan and Jason, who are doing our Ask an Astronomer later, are filtering through them and grabbing as many as possible to answer later on this evening. But yes, here right behind me is our original mirror. So it sits in the center of the universe. You can get a bit of a better view of it on our virtual tour if you check that out. You can see it from both sides, take a closer look at it. but we've still got it. The new one is the same size, but a bit lighter, so it's easier to move around.
So there's a note from Bill Weir that there is a 1.78 meter amateur telescope out there. So it's possible.
Mm-hmm. Let's see. Oh yes, our Ask an Astronomer team is also going to be typing answers to questions as they can as well. Let's see.
So how is the observatory keeping up with advances in technology? Clint asks that.
Oh,
who's going
Calvin,
to?
do you want to take that, or I can?
Hey, so the question was,
how is the observatory keeping up with advances in technology? So it's over 100 years old. Things have changed a bit.
Things have changed a bit. Most of what I showed in that virtual tour, the general structure of it, it's all the original stuff. But there have been important key technological improvements. One of them would be the digital camera, the charge coupled device, or CCD. Before that, they would use photographic plates to collect light and make an image out of. Now they've got basically digital cameras, and those collect way more light in a shorter amount of time. And so that really brought this telescope into a more modern age when that came time to do that. The other change, I think it was already discussed, that the original mirror is not, of course, the current mirror. There was a newer one that was made of ceramic instead of glass, so it's a little bit lighter and a little bit thinner and easier to use, especially because I think it uses aluminum rather than silver, which the aluminum tarnishes less often, so it needs to be resurfaced only once every few years as opposed to a few times every year. And I also mentioned the that it could be used for remote viewing as well.
All right, we have one or two questions from some younger viewers, not quite on the topic of the telescope, but ones that we won't be able to get to before these visitors have their bedtime. So let's grab one or two of those questions. Let's see. Jason, if you know which one they're looking for, you can pop in. I'm not sure which ones they were talking about.
So Dawn had let me know that Kaya, age 4, wanted to know, how did the moon form? So, and she won't unfortunately be with us when the Q&A actually happens.
I think I better answer this one. I'm the moon guy.
Yeah, give her.
So Kaya, there was a big collision about 4 billion years ago. So a very large, well, a small planet, a very large moon-sized thing, crashed against the Earth. And one of the things that ended up with there is the Earth got a little bit smaller, and the moon was formed, and it formed outside the Earth. And so it's the result of that big collision that then over time it became a nice, beautiful sphere, nice ball, just like the Earth, but it's part of the Earth originally. Next.
All right. If we have one more question from a younger viewer, we can go to that. And then I think we have just enough time to take one last look at the sun before we start our official programming. Let's see. Don't see another one from a younger viewer. Okay, let's see. David with the solar telescope. Do we have the sun again?
Yes, we're still here. David's just getting it on board.
Okay.
And
While
we
you're
have
doing
about
that
10
all,
minutes. We have about 10 minutes before the official opening.
yeah, so let's take another look at the sun quickly, see if there's anything new. I'll grab one or two more of these questions here. Peter asks, do we keep the CCD array for the telescope at room temperature?
Do a quick
So the CCD is the camera part of the telescope. This is the part that actually catches the light and turns it into an image. It's a very similar type of detector to the chip camera you have in your cell phone, or pretty much any digital device with a camera nowadays will have some variation on
well,
a
I was going to just do a quick share
charge capture device.
And then we'll go back to the sun.
The CCD on the telescope is chilled. The one we have two on there. We have one for imaging, and that one is cooled using a what's called a cryo pump, and it's kept at I think about -20 Celsius. And then we have a very, very sensitive CCD on our spectrograph, and that one is actually cooled with liquid nitrogen. Very, very, very cold, about -73 degrees Celsius. All right, so we've got the sun here. Looks like
actually, we have the moon.
That's the moon.
Oh, this is the moon.
So there are other things to look at during the day, and today, because we're not too many days after a new moon, and the new moon is a time of the lunar month when the moon is very close to the sun, and they're gradually drifting apart. So if you do go outside, you'll see the sun is getting close to the horizon, and the moon is up above it. And so we do have a camera on the moon, although it's very hard in this light to get a decent focus, but you can maybe see a little bit of craters to the south there, but it's they're not coming in terribly well. But I think we'll go back to the sun, which is more interesting. So I'll just stop my share there.
Okay.
And David will put up the sun.
Ooh, ah.
And there we are in the prominence view. So you can see the around the edges. And we'll zoom in and you can see that on the what is actually the right side of the sun, although we're seeing it on the left. There's quite a nice prominence along there.
For people who weren't there at the beginning, tell us what we're looking at.
Sure. So this is a telescope that can pick up the emission line from hydrogen, so reacting hydrogen. So you're looking at a cloud of hydrogen that is out to the side of the disk of the sun. And a lot of the time, these will also follow magnetic lines of force. So they often form loops and arcs and things like that as well. So basically, you're seeing a cloud of hydrogen there. You're seeing some shimmering there because we are getting low into the horizon and we're looking through a lot of atmosphere now. So it does shimmer. And yeah, what else can I say about that? So basically, when hydrogen reacts, it releases a light fingerprint apart from other things as well, other wavelengths as well. And this in the red band is its strongest line. So these are often referred to as hydrogen alpha telescopes.
And the thing I like is just how big those features are.
That is probably at least three or four Earth diameters sticking out there. So they have to be big for us to see them with this size of telescope.
That's so cool.
And I don't know,
We'll
one
move
last
over
look
to
at the
the,
sunspot. Or just move, which way would you like us to move?
Oh, just go to the to the sunspot view, the
Sure.
lower exposure.
Yeah. We shall do that. So again, when you're using a camera with this type of telescope, you need to basically kind of overexpose the disk of the sun to see what's going around the edge. But then you need to turn the exposure down and use a shorter exposure to see what's happening on the surface. So there we have the sunspot that we can see today. So again, this is quite a big sunspot. There may be others, but they're probably a bit too small for us to see if there are any others.
Okay, I think we've got time for one or two more questions here. David asks, how long does it take for particles in the center of the sun to bubble up to the surface?
One of the things, as I understand it, it's not all that really well understood, but it could be tens and hundreds of thousands of years.
Yeah, as far as I understand it, there are two rough layers of the sun. There's something called the convective zone and the radiative zone. The radiative zone is in the center, going out to about halfway out to the surface of the sun. And in that region, there's no convection. There's not a lot of mixing of material. It's just sort of hot and jiggling around. Whereas in the convective zone outside of that, the gas sort of loops through, goes down to the bottom, gets heated, and then bubbles up to the top. That's what caused those granulations we saw. And in that layer of the sun, stuff gets mixed around, but not in the core. So there isn't really, there's not really particles that make it from the center of the sun out to the edge. What does come out is the heat through photons, bits of light. So you get a photon produced by one of the fusion reactions, and that bounces its way around, gets split into lower energy photons and lower energy. But if you trace the path of one photon and its children, the ones that get split into, then those can take, roughly 100,000 years or so to make it to the surface. As well, Bill asks, and this may not be possible quite now, but is it possible to see the moon and Mars together right now, or is it still too bright?
Mars is too bright at the moment.
Yeah.
It's too bright for the Mars.
Yeah, we usually can't see Mars during the day unless it's particularly close to the Earth. We can sometimes see Venus during the day, but again, it's too close to the sun.
Okay. Well, we are doing some observing later on this evening, so hopefully we can get a chance to look at that later on. Okay. So 7:58. Let's see. Ooh.
Well, let's close off this hour with some acknowledgements. First of all, to our solar team. So that is David Lee and Sid Sadu and Chris Peirce. So they've been working hard to make sure that we can get this live. I think it's just fantastic that we've got this technology. So thank you very, very much. And then for the tour inside the dome, that's Calvin Schmidt, assisted with Ben Dorman. Thank you very much. And that virtual tour, you can go to the FDAO, the Friends of the Dominion Astrophysical Observatory, or actually the Center of the Universe website, and you can take that tour yourself, not with the excellent narration that we got, but you get to see around. So thank you very, very much for this. What do they call it in a hockey game? The pre-game show,
something like that. Yeah. And Calvin has just posted the link to our virtual tour in the Zoom chat. And I'm sure Amy is posting it on the YouTube as well. So please feel free to check that out.
Yeah, thanks, guys.
And I think we also have to put a big thank you right here at the beginning to Laurie Roche, who has been the fearless leader, coordinator, and birthday girl for this event today.
Absolutely. Okay.
It's been fun. Lots of great teamwork here for everybody. Thank you.
Excellent.
So do we have theme music to bring in the actual opening?
Oh, that would be awesome. I should have thought of that. All right.
Okay.
So let's get started with our official programming for the evening. So we have a few things to start with. Well, first off, we'd like to acknowledge the land we are broadcasting from. We'd like to take a moment to acknowledge that we are on the traditional territories of the Coast Salish and the Kwanghan-speaking peoples, who are the custodians of these lands and waters. This area has long been the gathering place of the Songhees, Esquimalt, and Wasyimic nations, long before the arrivals of Europeans. We're grateful to have the opportunity to live, work, and collaborate and learn here, and we respect the continued connections with the past, present, and future in the ongoing relationships with Indigenous and other peoples within the British Columbia community. We invite all of our attendees tonight to reflect on the relationships you have to the communities that inhabit this land and share the night sky in wonder.
Well, thank you very much. My name is Randy Enkin. I am president of the Victoria Centre of the Royal Astronomical Society of Canada. We are an organization that started in 1914 and has been operating continuously ever since. We have about, I think it's 250 members. We're always interested in having more. Our main operation, our main activity during the times of COVID is a Monday night Astro Cafe. And you can get information about that if you Google the RASC, Royal Astronomical Society of Canada, Victoria Centre, and you can get on our mailing list. It is just a wonderful pleasure to be able to celebrate International Astronomy Day together. Victoria is very, very rich in institutions and organizations that are doing astronomy and astronomy outreach, and prime among them are friends of the Dominion Astrophysical Observatory. So, Aaron.
Yes, actually, I'm going to pass over to Ben to talk about the Friends of the DAO.
Okay. Firstly, happy birthday, Laurie. Secondly, Friends of the Dominion Astrophysical Observatory welcomes you to this evening. This is our biggest virtual star party to date. We have about 135 people online here tonight, which is a record by a factor of 2 or 3. Friends of the DAO has been around for 6 years now. And we've gone from a couple of people thinking, sitting in a room wondering what we could possibly do, to an organization that is running all year round, attracting speakers and audiences. We have had a license to use the Plaskett Telescope and the Center of the Universe Visitor Center, where Aaron and I are sitting, since 2016 now, and we've been partnering with our great friends from the Victoria Royal Astronomical Society of Canada Center, who are instrumental in showing the public the sky whenever we can actually have them up here. We've been materially supported strongly by the National Research Council of Canada, who I should add another acknowledgement to the solar observers tonight, who bought us the telescope and the camera, and has been instrumental also in adding to the offerings that we can give to the public. We have 1 1/4 full-time equivalent staff in Calvin and Aaron, and Calvin is full-time, and he is usually to be found online, talking to school children and community groups and college students every day of the week that we can. We have managed to reach thousands of people in the last few years, and we are expecting to go as soon as we are unleashed from the COVID restrictions, which we've managed to get through pretty well. We're hoping to have more offerings. Some of them designed by our own Aaron Bannister, and some of them by our other board members like Dan Posey. And keep in touch with us. There's wonderful things still coming. Thank you.
Thank you, Ben. And now Amy is going to talk a bit about the FDAO.
Hi, everyone. Welcome. My name is Amy. We're so glad you could join us this evening. As you know, the Friends of the Dominion Astrophysical Observatory has joined forces with the Royal Astronomical Society of Canada's Victoria chapter for this evening. Both the FDAO and RASC are membership organizations, and I'll put in the chat window how you can find out about joining both of these groups. And I, of course, sorry. We have been able to continue school programs virtually this year. Our school programs allow students from across the country to visit the telescope virtually now. In the 2021 school year, to prioritize education, we have been doing these tours at no cost to the schools. So your donation dollars have helped to make these tours possible. I know some people have asked how they can donate to the FDAO. I will put that link also in the chat box. Your donations make it possible for us to bring you events like this one. Outreach and science education is, of course, at the core of what we do. If you're interested in helping us through volunteering or monetarily, it is all so appreciated. You can reach us at info@centeroftheuniverse.org. I'll put that in the chats as well. Yeah, every bit of donation helps. So thank you so much for your support and for attending tonight.
Fantastic. Thanks, Amy. All right. So next up, I just have a little bit of housekeeping for the evening before we talk about our schedule. So this is a Zoom webinar, which is a little different from our meetings that we've had previously, if you've attended any of our Saturday night star parties. And it's probably how we're going to run these things going forward. We may go back to the meeting format, but since we are doing this and it's much larger, we've got a few things that'll help streamline things. So first off, if you have a comment during the evening, you're welcome to post that into chat. But if you have a question and you want to make sure it gets answered, please do use the Q&A feature. So that's either going to be a button that pops up when you tap your screen if you're in mobile, or it'll be accessible from the 3 dots menu down at the bottom of your screen if you're using the desktop version of Zoom. That question gets sent to us and it gets preserved there so that one of our team can answer it through text, or we can answer it live. We may, if there's a question that's a little far-reaching or that's not quite on the topic, but we do want to get back to it, we may dismiss your question. What that means is we're storing it off to the side, so our team for the Ask an Astronomer panel can come back to it during that section of the show. Both the chat and Q&A are going to be monitored. We're also going to be grabbing any questions that come in through YouTube and adding those to the Q&A. So if you are watching us on our YouTube live stream, please feel free to ask any questions there as well. They'll get passed along. And then finally, I'll ask all of our panelists to keep your audio off unless you are speaking right then. Do be sure to unmute though before you say anything. I've left myself on mute a couple times already this evening. As we go over the program for today, I'm going to start a poll. We'd just love to hear where folks are coming from this evening. So I'm going to post that. If you are on Zoom, then you should be able to see that popping up right about now. And then we'll, while folks are looking at that, I will pass things over to Randy and bring up our schedule.
Well, actually, I'm going to bring up the schedule. Ha!
Ah, okay.
I beat you to it. There we go. Except there's a window in front of my share button. There we go. So I hope you enjoyed our pre-show, looking at the sun and inside the dome. Next up in 5 minutes is our feature speaker, Kim Venn will be giving us a talk about fossils in our galaxy. After a question period with Kim, then we're going to have a tour of the University of Victoria Observatory. And then we're going to have a Ask an Astronomer. And let me just say that if you put in the Q&A, it will get answered then. After that, then we have Constellation Story. And we're going to be going between that and these beautiful pictures that have been compiled from members of the Royal Astronomical Society. And then, weather permitting, this is very strange. I think every single FDAO star party since October, that's one Saturday a month, has been clouded out. But the star gods, the weather gods are looking favorably upon us. And so we'll actually get some live streaming telescopes this evening. So that is very, very pleasing for all the organizers and people who've been working hard on it. And it's just going to be a lot more fun. So we hope that you enjoy the show. We certainly have enjoyed putting it together.
Excellent. I'm just sharing our poll results here. Looks like we've got a whole bunch of folks from around Victoria. Always great to see. With about 25% of folks coming from outside the area, from outside BC, or and a couple even watching from outside the country. I wonder if those folks are from the US or elsewhere in the world. Please, if you are from outside of Victoria, we'd love to hear where you're visiting us from in the chat. All right. Now let's turn things over to Ben to introduce our speaker.
Yes, hello again. It's my pleasure to welcome one of the most accomplished astronomers in Canada, as well as someone I've known for many years. Kim Venn is originally from Toronto and got her bachelor's in physics and astronomy back from there. She had a PhD in astronomy from the University of Texas at Austin and came back to Canada in about 2004 to come to the University of Victoria. She has a specialty in stellar spectroscopy and in the chemistry of stars in our galaxy. Tonight, she's going to talk to us about the fossils of our galaxy, the stars that we know of that show a real possibility that they are the oldest objects because of what they're made of has never been enriched by the kind of chemicals that are made in later generations of stars. So without further ado, I'm going to pass you over to Kim, who I hope is unmuted by now, and let's go.
All right, will I be able to share my screen?
You should be able to.
Okay, great. Great, and
yep.
Is this a go?
Yep.
Yay! Oh, wow, look at that. We already fixed the first bad trick. Awesome, everyone. First of all, Ben, thank you so much for the opportunity to come and give this talk, and also to participate with you with the Friends of the Observatory. I'm really, really pleased to see so many former students. Hi, everyone. It's really great to see you all, and also some current students. So that was really unexpected pleasure. And maybe some of you even recognize this front picture that I'm using. It came from the UVic Astrophotography Club. I think there was a camp out. That's Nick Anu in the background. I don't know if some of you guys were on that trip, but I really love it. And so I actually use it even in, for many of my talks. So so thank you so much. And actually, I thought it was completely relevant for this talk, because I will talk quite a bit about the Milky Way and show you the plane of the Milky Way galaxy frequently. So I thought this was a great one to start with. I do want to say as well that one thing I've learned already is that as I get older, I probably need to be more careful with my talk titles. So, but this one was Ben's, and Ben, I blame you. And I know you and I are about the same age, so we have known each other a very long time. And so I was also going to do a land acknowledgement, but Aaron, my God, you just knocked it out of the park. That was beautiful. And I would say very much the same thing. When I do a land acknowledgement, I also like to note why we do it. And you did that as well, which I'm so grateful for. I think that was really important. I do want to say that I think it is important wherever we are to acknowledge and be aware and respect the Indigenous communities on whose lands we are fortunate to live and work. I also, especially over this past week, have been trying to explain the importance of the actions recommended by the UN Declaration on the Rights of Indigenous Peoples, which Canada signed in 2016, and which has led to a lot of our Indigenous planning at the universities, as well as within our communities. And so I think that knowing these things are important, and hopefully more actions will come. All right, so getting back to this talk about fossils, and I want to start with, again, this also beautiful picture of the plane of the galaxy, this time, of course, from the southern hemisphere. And if you couldn't tell from the Magellan telescope that's in that picture down there, which is in the south, then you certainly would have realized it from the Magellanic Clouds that are over there on the left. And when you look at a beautiful image like this, after noting the Magellanic Clouds and the Milky Way, and then all those other stars, which of course are fairly nearby, otherwise we wouldn't see them as bright and individual stars, then I hope that you'll see what I see after that, which is just fossils everywhere. Fossils, wherever you look, it's all fossils. And if you don't see them now, I hope you'll see them within the next 20 or 30 minutes. So, so to see that, then what is really necessary is that I explain where they're coming from. And where they're coming from is the latest data release from the European Astrometric Space Telescope called Gaia. Gaia has been working in combination with ground-based spectroscopic surveys. And then together, these are leading us to see the galaxy a little bit differently. And that's what I want to share with you today. And what I think is so interesting is it's one of the few times when these images of just these pictures, just straight up magnitudes of the stars, actually isn't what we're working with. We're working with something else. So Gaia is an astrometric satellite. And for those of you who aren't very familiar with that, it means it measures the positions of the stars relative to background stars. It was launched in 2013. And the third data release was recently sent out in December 2020. So very, very recent. It's still up there. It's taking data right now. And what's beautiful, it's been running now for 8 years. It still has 2 more years in its extended initial mission timeframe. And because of the long time frame, it includes multiple measurements of the same parts of the sky. And therefore, it's actually not only able to measure the exact positions, as well as parallax, right, the apparent motion relative to background stars due to our motion, but it's also actually able to measure the real motions, the real proper motions of stars on the sky relative to background objects like distant quasars and galaxies that don't appear to move. So, what's exciting about this third data release that happened just in December is that the data volume now goes all the way from the galactic center to 8,000 parsecs, or roughly 25,000 light years in the opposite direction towards the anti-center as well. So if I'm going to share with you all of the really cool stuff that Gaia has done, then I also would like to share these motions on an image of the galactic plane that doesn't matter whether you're in the north or the southern hemisphere. So I want to project the gorgeous image of the galactic plane onto the whole sky using something we call an ATOF plot, but it's very similar to what we do with a world map. So you can see every star, everything on the plane just in one projection in 2 dimensions. Sometimes what I say is if you took both sides of that projection and wrapped it around your head, you'd have the sphere and the whole sky around your head. So we're going to project onto this 2D map to see the distributions of stars and their motions. So I'm hoping that this is a video for you. So wait for it. It might be a bit faint, but you should see some of these stars moving. This should just not be just a gray image. And if it looks like, if you're not seeing stars moving, maybe turn some lights out or something. This is a video. And I think that this is, the first time I saw this, it was released with the first data release a few years ago, 2 million stars. And it's using the Gaia positions to track where the stars are going to go over the next 5 million years, which is amazing. So from the Earth's point of view, you can actually see how the sky is going to change, how the constellations are going to change, thanks to these precision orbits and precision measurements from Gaia. If you watch this video right to the end, you can even see an imprint of how the galactic center, the plane's going to change because of the Earth moving along in its orbit as well. But this goes for 5 million years, and why don't we go to the next one instead? So there was another video that came out, and I really love this one as well. Wait for it, it'll start. As the stars start to move, it's actually tracking them. You know, sometimes it's hard to see those individual little stars moving around those videos, but you can see the arcs. You can see the arcs that follow them in their motions, and you can see those stars near us are just moving all over the place. Some of them are moving towards us, some away from us, some to the left, some to the right, but it's just this like fantastic view of a movie of what our galaxy is doing. So what I think is also where I want to go with this as well is not only this amazing movie of our galaxy and the sky that we see, but also once you can get orbits like this, you can start to look for groups of stars that orbit kind of in the same way, but may not be on the same part of the sky anymore. And if we can find those, then what we're finding are disrupted globular clusters, disrupted stellar clusters, disrupted galaxies that have been merging with our galaxy and are now out there in the halo or wherever. And so that's what I want to talk about next is finding groups of these objects to disentangle things that have merged with our galaxy at older times. So the first one of those that I want to talk about is the Sagittarius Dwarf Galaxy. Now this one actually was discovered before Gaia. It was discovered back in 1994 just from deep imaging with the Sloan Digital Sky Survey. And if you look in the little inset right at the very bottom there, using different filters, it was possible to pull out this little faint satellite galaxy that's merging towards it looks like it's merging into the center of our galaxy. It's actually all the way on the backside of our galaxy and moving through. And this Sagittarius Dwarf Galaxy merged with our galaxy about 6 billion years ago. So it's much, much smaller than our galaxy, about 1,000 times the mass of our galaxy. And it's in an orbit, and we're finding stars in long streams all around, and that's kind of the core of it, just under the center part. And that one was easy, even though it was not easy, but it was easy because those stars are actually fairly closely grouped together in order to find it in the first place. Nowadays, though, with Gaia, we're finding groups of stars that spread across the whole sky. So they have really similar orbits, similar directions, other similar properties that we'll get into later. And these are the things that we would not have been able to find without something like a proper motion machine that can get us the orbits of the individual stars. So this is how Gaia Enceladus was discovered. It's likely the largest collision to have happened in the last 9 billion years or so. It happened about 9 billion years ago. And there's still some controversy over whether it was one galaxy that came in or maybe a small group of them, sometimes called Gaia Sausage, Gaia Sequoia 1 and 2, and then there's a few other names for it may have been a little cluster of galaxies that came in. And I thought what was beautiful in preparing for this talk, I hadn't actually seen this slide before, but I thought it was really lovely. It's an analysis published in August of 2020, very recent, and it suggests that the Milky Way has actually had several of these mergers, not just Sagittarius and not just Gaia Enceladus, but several of them. Look, all of them have excellent names, right? You can see them across the top there: Sagittarius, Sequoia, the Kraken, the Helmi streams, and Gaia Enceladus. And And the idea is that they were merged at different times. So this is if you I don't know if you can see my cursor, but it's time going down. And so the Milky Way galaxy would have been a tiny galaxy, and then through mergers at very early times, it would have grown in mass. And then the Kraken came in, and the Hellner-Mestelman came in, and Sequoia came in, Gaia Enceladus, Sagittarius, and maybe even some things have been accreted after that. And what's really interesting about this is the timing on the accretion of Gaia Enceladus and Sequoia is roughly similar to the age that we think the disk of our galaxy is. So this beautiful disk that goes through here is not as old as the galaxy. It actually seems quite young. It's about half the age of the galaxy, roughly. And so, you know, there's some questions about how the disk formed in combination with these incoming galaxies, and can we disentangle that with things like proper motion? So I thought that was quite beautiful. The other thing, though, that's interesting is that these galaxies, which seem to be the ones we've been able to pull out, actually only contribute about 1 billion solar masses of the hundreds of billions of solar masses of stars in our galaxy. But they're a collection of some of the most interesting stars that you could ever meet. They came from another galaxy. They didn't form in our galaxy. We accreted them later. And looking at differences between those stars and stars in our galaxy tells us a lot about chemical evolution and of the universe, as well as how things have formed after the Big Bang. So that's where now you're starting to see probably where I'm going on with fossils, why this is called Fossils of Our Galaxy. And I want to be clear about one thing. Of course, this is not the first time that we've discovered galaxies merge. We've known this for quite a while. I mean, there's tons of gorgeous images out there taken from the ground as well as from Space Telescope. But what's new is finding these remnants that built our galaxy. So these remnants are ancient mergers that contributed to what our galaxy looks like. And that's what's interesting, because of course our galaxy is what led to formation of our sun and our Earth and us. And so this is what's exciting about Gaia, about the Gaia mission. All right, so moving on just a little bit then. When I showed you those videos, which I think are spectacular, if you notice, all those stars look the same. And as you know, all stars are not the same. And this is because when we're talking about just the motions of stars, we don't really worry too much about the detailed properties of the stars themselves. If we're not, though, if we actually want to know something more, like if we find a stream that's together and we want to know more about that stream, or was it a dwarf galaxy, was it a globular cluster, was it, how old is it, what is it made of, then we want to know something about the stars themselves. And so, as you know, stars come in different magnitudes, they come in different colors, they come in different masses. And so I want to show you one more of these beautiful Gaia videos. So first of all, also just this globular cluster is gorgeous, isn't it? NGC 2699, NGC 299 from a Hubble Space Telescope image. Those bright stars are all at the same distance. So some of them really are redder, some of them really are bluer, and some of them really are brighter, and some of them really are fainter. So so if we watch this video now, this is it takes a little time to get going, but it'll get going. Because what we're doing is we're moving out from the sun at exponentially increasing speeds. And what we're going to do is move out from the sun and then collect stars that are only within the solar neighborhood. So in this picture, you can see all the stars as we've moved out from the sun that Gaia has observed. And now we're getting a ring that's about 400 light years, or about 122 parsecs. So that's just a tiny fraction of the full Gaia sphere. But it gives us a really good idea of the total stars that are within our solar neighborhood, within roughly 100 parsecs or 400 light years of our solar neighborhood. And if you divide them up by luminosity, because we know the distance from Gaia, we can get them by luminosity, their intrinsic luminosity, and then we can divide them up by color as well. And you can see that if you just use the same, for those images, the same color for all the stars, you can't tell any difference between them, but they are different, but they're not randomly different, right? They actually lie in a very particular way, in a very particular relationship between their intrinsic luminosities and their intrinsic colors. So I love this plot, and I'm going to come back to this plot in just a moment. Just a reminder again, this was the full Gaia sphere, this 8,000 parsecs, or roughly 25,000 light years. And we just looked at roughly only 400 light years, just a tiny, tiny little region in the sun. So really just a solar region. But what's beautiful, and I just want to emphasize this because I'm going to get back to that plot in just a second, is that because Gaia has such a large region that it's looking in, it can get stars all the way into the galactic center, which is important. I'll show you why in a moment, as well as all the way to the anti-center and perpendicular up and down in the galaxy as well. So those disrupted galaxies that may be polluting our halo or disrupted globular clusters, they will pass through the Gaia sphere. So that's a way to start looking for those fossils or accreted galaxies in our galaxy. So going back to that last plot from the separation of brightness versus color, what we do know from studying stellar physics is that the stars on the upper part, the brighter and bluer ones, are higher mass, and the ones that are fainter and redder are the lower mass objects. And then this track off to the left here are the white dwarfs, they're evolved stars, so different again. And if we focus on just the upper part, we actually know even more. So if we focus on just this upper part here, just up here, and we look at just this fan, now remember this is only in the solar neighborhood, but if you go over that 8,000 kiloparsec, 8,000 parsec radii sphere, so even larger, 16,000 kiloparsec sphere, parsec sphere, or whatever, sorry, then you get a lot of stars that distribute along that little fan off to the side. And when we start to look at that fan with more details, so with more colors, meaning more filters, images with different filters, or even better with a spectrum, a stellar spectrum, then we can start to separate out those stars also according to their age and metallicity. And this just gives you an indication that if things are more metal rich, they are quite a bit redder, they're over to the right even more. And if they're metal poor, they tend to be well over there to the left. And this is incredibly helpful for trying to look at the the change in chemistry as the universe has evolved by looking at stars at different ages, meaning the fossils of previous star formation going right back to the Big Bang. And if I'm going to talk about chemistry, it is very, very important to share with you, or make sure that you've seen before, the astronomer's periodic table. So most astronomers, unlike most chemists, will see chemistry and all the chemical elements as hydrogen, helium, and everything else, which we just lump into a group called metals. And this is because 99% of the universe is made of hydrogen and helium, so fair point, fine. But it's that 1% of metals that can tell us so much, that can provide us with observational tests of cosmological models. And if our universe really did form in a Big Bang, we have tests of what the chemistry would have been like right after the Big Bang. We think it was just hydrogen, helium, a little bit of lithium, and nothing else. And then everything that's happened since then is the evolution, the origin of the elements and the evolution due to the evolution of the universe. So if we put this all together, if we're looking at the evolution of the universe, it starts with just hydrogen and helium over here in the Big Bang, maybe a little bit of lithium. And because the universe was expanding and cooling so quickly as hydrogen and helium were forming, then the cooling meant that that other heavier elements couldn't form. So as the universe is expanding and cooling, the hydrogen and helium are spreading apart, not coming together to make heavier elements. So it took gravity to pull all this together. And so after some time, when gravity was able to start to work inside of dark matter halos, then gas would have accreted into those dark matter halos as well. And once gas can accrete, then you can start to form stars. So we think there would have been a generation of first stars. Those first stars would, some of them would have evolved and put their gas back into the interstellar medium, forming the next generation. And some of those would evolve and put their gas back in the interstellar medium, forming the next generation, and so on. And all of this is happening, we think initially, just in the universe en masse, but eventually collected inside of galaxies. So once we had stars forming, then we had some engines where we could make heavier elements. And so basically this latter part of the evolution of the universe is really about following star formation, galaxy formation, origin of the elements, and then chemical evolution right up to the point where you can make something like the sun, which is capable of making something like the Earth, which is capable of hosting something like us. So as we go back in time, and these rings here in this image are time. So we think the universe is 13.7 gig years old. So this is roughly the 14 gig year age line, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, bam. And so if we can go back, then what we really want are stars that are older than the sun, if we're going to be treating these like fossils that are going to tell us about the origin of the elements. And so just for perspective, the sun is about 4.5 billion years old. Of course, that's when the Earth formed as well. The oldest fossils on Earth are the stromatolites at about 3.5 billion years old. The oldest animal fossils are the trilobites at about 500,000 years old. Sorry, 500 million years old. And so the stars we're really interested in are the ones that formed sort of in the first few billion years. And even the ones, you know, the very first ones would be really nice to find, but we've never found those. So anything that's metal poor, very, very metal poor, probably formed just shortly after that. Maybe it was enriched by only one star formation event or one supernova or just one thing that contributed. And that's what we're trying to find. We're trying to find things like that that can tell us about the origin of the elements and what the universe was like at the earliest times. So, I mean, it's just amazing to think that some of those stars that are whipping around in our sky right now, you know, one of them could have been formed right after the Big Bang and be carrying a record of what our galaxy and what the universe was like at that time, you know, going right by us right now. And what's so great about that is that while we can do a lot from imaging and a lot from spectroscopy, it's shockingly difficult to find these metal poor stars. There are billions and billions of stars out there, of course, and as you get larger telescopes, you can go fainter, so there's even more that you can see. And very, very few of them do we know the chemical composition or even have an estimate of what their chemistry is like. And so we have no idea of how many metal poor stars there are, how many old stars there are. So this is kind of the fun part now, where we're at now. So when we look at these sorts of beautiful images of the sky and you know, beautiful where the stars are, none of that contains information about the chemistry of these stars. Absolutely none of it. What we need to do is something else. So these kinds of maps come from things like the Sloan Digital Sky Survey. From the Sloan Digital Sky Survey, we do know that metal poor star, which includes roughly 500,000 stars. And from that, we know that these very metal poor stars, the ones that are going to tell us about the beginning of the universe, are really, really rare, less than 0.1%, super, super rare. So if we're going to find those things which can tell us so much, we need to do something dedicated. And so I have been very grateful and very fortunate to work with an international group that originated here in Victoria to find metal poor stars. We call ourselves the Pristine Survey, and we use the Canada France Hawaii telescope with a very specific filter that took us quite a while to come up with. We benefited immensely from work that was done by an Australian group trying to do the same thing, find metal poor stars in the Southern Hemisphere. We benefited from their trial and error. And so we're able to define a very unique band. It's very close to the calcium H and K lines, if you know those in the solar spectrum. And when combined with other specific filters from the Sloan Digital Sky Survey or also from Gaia, then we've been able to successfully calibrate the metallicities of stars down to 1/100th and even 1/1000th the metallicity of the sun. And that is the kind of metallicity, those are the kinds of stars that we think would have formed at early times and we're really interested in now. So I'm showing you this plot because it's not exactly the same projection, but it's close. We have in the gray area is where the CFHT Pristine Survey has been happening. And on top of that, what we've added is information from Gaia on where we think there are streams. So, you know, streams of stars that have similar orbits, You can see that you can see some of them really look like they're lined up with similar orbits. And so when we combine Gaia streams with our pristine, you can see we really haven't covered very much of the sky, but with our pristine metallicity, we have started to find some very metal poor streams that are pretty interesting. And in particular, one of them, this one way down here, has really caught our attention because the data points in those streams are correlated to their metallicity. So the darker they are, the more metal poor they are. So this looks like a very metal poor stream. And when we followed up with the GRACES spectrograph, which was built here at NRC by the amazing John Pasder, which is at the Gemini Observatory, and it feeds, it's a 270 meter optical fiber that feeds Espidons at the CFHT. We combined GRACES spectroscopy also with OSIRIS spectroscopy from Granticon on La Palma. Then we were able to prove to ourselves that at least 9 members of this stream are extremely metal poor. Metallicity that is on the order of 1/300,000th the metallicity of the sun. And because there's 9 of them, and they also had a few other chemical abundances that strongly suggested they're a globular cluster, then we compared that to other known globular clusters, the metal abundance in the other known globular clusters, and found that it looks like it's almost a factor of 10 lower than any other known globular cluster. Now, and it seems to be disrupted. So we're about to submit this to Nature. And I just wanted to say, if you have worked with globular clusters, you would know why this is exciting. If you haven't, I just want to say this is important because cosmological models make a prediction of the lowest metallicity permitted for globular clusters to form and survive 13.5 billion years or 12 billion years to this day. And this one is far, far below that. So it really raises questions about, do we actually understand how globular clusters form? And or why did this one survive? And so this is, the Nature paper is just the discovery of it. The follow-up is going to be super, super exciting, I think. And then, as you can see, we're just starting to scratch the surface. Combining Gaia data with our pristine survey, we expect will show more of these. I wanted to show you one other result that I think is super interesting because it comes from Federico Sestito, who has just arrived here in Victoria as a postdoc. And what this is it's an odd plot, but the axes are actually different ways of combining the angular momentum of the orbits of the individual stars. This is the orbits of all of the most metal poor stars that we have been able to find in the pristine survey and confirm with spectra. So every one of those data points is a metal poor star. There's a couple hundred, I can't remember now. There's a couple of hundred of them. And I think what was super interesting, what we were very surprised by is that some of them are prograde planar and some of them are retrograde planar. What does that mean? Well, prograde planar means that these are stars that are orbiting in the galactic plane in the same direction as all the other stars in the galactic plane. Great, that's what you would, you might expect some of them, but these are very metal poor, which means they would have been older than the galactic plane itself. So that's a bit odd, but fine. But what we found is that there's a large number of metal poor stars that are in exactly the opposite direction in the plane of our galaxy and actually traveling at about the same speed, but in the opposite direction. And so I like to think of it as like an English person when they come to Canada and they rent a car. Oops. And so needless to say, these stars came from somewhere else, right? They had to have been accreted in something, some sort of dwarf galaxy at some time. And maybe because there's such low metallicity, maybe these were amongst the things that deposited gas into our galaxy, into the plane of our galaxy in order to make the disk. And then, of course, the disk of the galaxies we see today. So I thought that was super fun. We are, part of what Federico will be doing here as a postdoc is following up on those objects to see if we can find other chemical signatures in them that would suggest they came from one object or maybe multiple objects. No idea at the moment. And I thought I would just show you one more result, and then this is my last result slide, is that the pristine survey is also now just starting to look into the galactic center. So we just are beginning to believe that this little filter that we have can be combined with other filters successfully to find metal poor stars. And the galactic center is the hard part because well, actually, it's a hard part because there's so much gas and dust and young stars in there that to find these metal poor stars is going to be like a needle in a haystack. But it's a great place to look because the galactic center is the center of the potential that our whole galaxy formed in, the dark matter halo that our whole galaxy formed in. And so that's where gas would have accreted first. And so if the first stars formed in our galaxy, and if some of them had small enough masses that they still exist today, then that's probably where they're going to be. So we're just getting started on that project, partially with the Grace's, Gemini Grace's spectrographic game. And I just want to say this work is just underway, and I really hope that I can tell you more about it in a couple of years. So my summary slide, what's coming next? You probably know that the JWST is due to be launched anytime, and first light and first stars are one of the science cases of JWST. In Canada, we're also super interested in Castor, a UV spectrograph, imaging plus spectrograph telescope that also would be exquisite for studying these very metal poor stars. Most of the spectral lines in metal poor stars are in the UV, not in the optical, and that's how we can identify them in the first place. Also, the 30-meter telescope and the square kilometer array both have cosmic dawn and first light as one of their main science cases. And also something that's really relevant to this is multi-messenger astronomy, meaning things that transients and things that vary. And so neutron star mergers, black hole mergers, and which also give rise to gravity waves can be detected through transient timing, in part with the LSST, and also ultimately perhaps with the space-based gravity wave detector LISA, because these neutron star and black hole mergers, we also think of the things that form the heavy elements like gold and platinum and uranium in our universe. So it's fair to say, and this is my summary statement, it's fair to say that the future looks bright no matter what wavelength your eyes work at. And I shall stop there. Thank you.
Thank you so much, Kim. Let's see. Thank you. That was an amazing talk. And I got to say, it's I took your stellar physics course, oh gosh, 5 or 6 years ago now, and I think you were just starting to find some of these stars at that point.
Yeah,
so it's
right.
really exciting to see how far the research has come since then.
Oh, yeah, thanks, Aaron. So you're a little bit quiet. I think that's what Dawn was saying, and I find that too.
Is that any better?
Yeah, that's better.
Okay. Sure. Okay. I'll speak up for the moment. Yeah, we have one question from Dawn here. Omega Centauri is thought to be the core of a dwarf galaxy that was disrupted. How confident are we about that, and what do we know about it? Remember this coming up.
Yeah. You said Dawn asked that? Was it?
Dawn Moffat, yeah.
Okay. Oh, ask a hard question, huh? Thanks. Yeah, so you're absolutely right. Omega Centauri is the most massive globular cluster in our galaxy, and it has the biggest diversity of stars along its red giant branch. The fan that was at the top, and it's a bit of a mess. Absolutely, it looks it looks like it is slightly elongated as well, so we don't really see it as a stream, but it looks like it's embedded in the I think it's embedded in. Is it the Sag stream? No, it's not embedded in Sag. So but it's embedded in its own stream, and so it really does look like an accreted dwarf galaxy. The problem is that as some of you might remember, is it doesn't have all the properties of a dwarf galaxy. So we see many embedded groups of stars or streams that are from dwarf galaxies, like the Sagittarius dwarf galaxy. And what's fantastic is that when we study the model of them, we find that they must have been confined by more dark matter than baryonic matter in the stars, whereas Omega Centauri is not like that. It does not show the same dark matter content you would expect. So that's where we're at. It still looks like a multiple population and very massive dwarf galaxy, but it does not have the dark matter content that would make it a clearly defined dwarf galaxy.
Okay. To follow up on that, and this may be going a little far afield, but we have seen some dwarf galaxies that have astonishingly low amounts of dark matter. Could Omega Centauri have been something like that before, or?
I think it's the other way around. The dwarf galaxies have astonishing large amounts of dark matter, like crazy amounts, like 1,000 times the lit matter. Yeah, it's the globular clusters that have it's the globular clusters that have about the same amount of dark matter as baryonic matter, and so that's why Omega Cen still would fall into the normal globular cluster distribution for baryonic to dark matter, but its chemistry and its stellar distribution not at all. So yeah, no, it's a great question.
Thanks to Dawn on that. Yeah. Let's see, got a couple more here. Megan asks, what may have caused some of the older metal poor stars to orbit within the plane in one direction and others to move in retrograde motion within this plane?
Yeah, isn't that crazy? Isn't that absolutely crazy?
Yeah.
I mean, it really does remind me of
in the plane too.
Yeah, in the plane. So that we were not expecting it. So some people will say that if you have a normal halo and you took the disk out, of course you'd have some stars that are, and it's a normal halo meaning that it doesn't have a preferred rotation, then some stars would have to rotate prograde and some retrograde. So take the disk out and you're always going to have some. But the numbers we're finding are just so much higher than what you'd expect from just a normal spherical, isothermal sphere distribution. So that's why it really implies that the plane of our galaxy is the orbital plane of some accreting system or systems. And at least one of those systems got away and maybe came in at the opposite angle and ended up going in the opposite direction. Yeah, it must have been crazy.
I wonder if there could have been some event early on that made something like the Cartwheel Galaxy, where you have spirals coming in opposite directions or something, spinning in opposite directions.
It could have been. I mean, I don't know if you've seen, I don't have the slide of it, but for Sagittarius as well, when they plot the orbit around our galaxy, you can actually see like two sides, and it's been suggested that those two sides might have been the spiral arms from either side as it came in, because the closer spiral arm would have felt a larger tidal tug, and so that maybe that's why you end up with these two streams, which I think is quite interesting. The models on them are not definitive, but certainly consistent.
Very cool. Let's see. We have one from Bella, age 10. How many metal poor stars do we know about currently?
Oh, that's such a good question. So the really interesting ones, the ones that have at least 1,000th the metallicity of the sun or lower, it's only maybe 100, maybe. If Federico were on the line, he could tell me exactly, because he knows every one of them by name. But I think it's on the order of actually, sorry. It's on well, it depends on where you cut it off. At 1,000, it's a few hundred. At 1/10,000th, it's less than 15. And so those kind of 15 stars are really, there's a lot of science that's being done with those 15 stars, looking at different kinds of yields of chemical elements that you could get from supernovae, different kinds of yields of elements you could get from binary neutron star mergers, depending on what the masses of those neutron stars are. So super, super fun. Those are really, they're just, they're really rare and they're really useful. And so yeah, we're looking for them.
Yeah. Let's see. We have one question that asks, you mentioned on the slide that showed the retrograde and planar grade orbits, or I guess prograde orbits, that the former might have contributed gas to our galaxy. Why wouldn't the prograde stars have done the same thing?
Yeah, they definitely would have. Yeah, they all would have brought in gas. Yeah, sorry, I misspoke if I implied only the retrograde. Thank you for asking that question and getting that corrected.
No problem. Always good for clarifications. Let's see. Sean asks, is a low level of metals the only indicator for fossil stars?
Yeah, pretty much. No, by low metallicity, that's our first indicator. And then we look at specific element ratios. So I go back to being a chemist and not just an astronomer once we start to look at specific element ratios, as all my students know, because I make you guys work on that.
Yeah. Okay, we have, let's see, two last questions here. Two in the chat that are similar. So Andy and Chris are asking about the distances to these stars. Are they all in the Milky Way? At about what distance?
Oh yeah, no, that's a great question. So all of those 15 stars are all fairly bright. And so the distances, sorry, I don't want to make it up. So the distances are closer than the galactic center. So about half between us and the galactic center. So within about 4 or 5 kiloparsecs, but not necessarily in the plane. They're usually more in the halo. And we've only just recently found a few that are very metal poor in the galactic in the galactic center, and so that's kind of where we're quite well. Actually, any of them would be exciting from anywhere. So as Gaia goes deeper, then we're finding them further out. That's why we expect to find more, because of course the deeper you go, you can find more. But the ones in the galactic center, we've just started to find ones that look like they're very metal poor in the galactic center, and we're super excited about those. The problem is that everything goes through the galactic center. So things from the halo go through the galactic center, and globular clusters go through the galactic center, everything. And so you have to be really careful about what's just passing through and what actually may have formed there. And that's kind of the tricky part where we're at the moment.
And that's why you need Gaia to get the actual trajectories of those stars, not just the distances.
Exactly. And Gaia just in this last data release in December 2020 is the first time it reached the galactic center with reasonable errors. So so the next data release, which should be next summer, and then there'll be one more after that, should have quite good precision.
All right. Okay, I think this last question may take us, it might be a little long. Maybe you can give like a 30 seconds on what is the mass of a first generation star, the type you're looking at that will survive 13.5 billion years?
Yeah, absolutely. Absolutely. You know what you're talking about. Thank you for that question. I didn't go into that at all. The mass has to be less than on the order of 0.8 solar masses. Hey, Ben, you should mute yourself. Thank you. It has to be on the order of 0.8 solar masses. Otherwise, it would have evolved and gone supernova or explode as a planetary nebula by now. So that's absolutely right. And so this is definitely part of the questions. Ben, thank you.
Yeah, sorry, I'm trying to mute him. He's not actually sitting at his computer and it just keeps on muting.
It's okay. He's getting me back for something I did to him in Italy once, I think. No, I'm kidding. Anyway, so the question is excellent, because there's a real question: how do you even make the first stars? Like, how do you shove so much hydrogen together that it stays together and becomes a star, rather than just heating up and expanding? And so the way to overcome that probably is to have very high mass. So the first stars may have all been super, super high mass things like 10 to the 4 solar masses, types of stars we don't see anymore, because we have metals that actually help to cool gas in order to help them overcome and become stars. And so it's possible that the lower metal, the long-lived ones, the lower mass ones, didn't form right with the first stars, but there should be things that formed just after it, that weren't enriched in too much. So we're still interested in those. Maybe we won't ever be able to find an absolutely metal-free star, but finding something that's close to it should be possible. And there's really only one at the moment. It's sometimes called anyway. There's really only one, and we're all kind of shocked that there's still only 1. And as you know, in astronomy, right, the only numbers that are relevant are 0, 1, and anything. So we're still waiting for anything on that one. We're still at 1.
All right. Well, I would love to pick your brain for ages, but I think we've got to move to our next item.
Thank you very
nice
much,
to see you
Kim.
again, Aaron. Oh, thank you, Aaron.
Thank you
Aaron,
so
it's
much.
really good to see you again. Calvin, good to see you again. Jason, good to see you again too. Thank you everybody for joining. And Randy, I should pass it to you.
Yes, and that was just wonderful. I learned so much. I'm a Gaia fan, so getting to see it is super.
Great, thank you.
So as we continue this International Astronomy Day extravaganza, I'm very happy to invite Marjie Welchframe, an artist in our Victoria Center, who is going to introduce a 4-part series that we're going to be showing interspersed with the other things coming up. Marjie.
Thank you. Good evening. I'm Marjie Welchframe, Second Vice President of the Royal Astronomical Society of Canada, RASC, Victoria. The Royal Astronomical Society of Canada, Victoria, astrophotographs and sketches, which you will view this evening in 4 separate groupings, have been selected to inspire and to generate a sense of exploration. All the images have been created by the Royal Astronomical Society of Canada, Victoria members. We want you to savor what they and you are able to observe through the lens of a camera or telescope. Some photographs record deep sky objects. Others document easily accessible naked eye objects, such as the sun and the moon. Some subjects require hours to capture and to edit, while others, created as sketches, are an immediate reconstruction of a viewer's experience. How were these slides chosen? With a view to selecting a diversity of subject matter, on the ability of the slide to catch an observer's eye, on the excellence of the finished product, and to open up the world of astronomy to all. These slides represent just a small portion of the talent and passion of the members of RASC Victoria. Thanks to Jeff Enns, Waterloo, Ontario composer, for permission to use his music, I Carry Your Heart, set to text from an E.E. Cummings poem, and to Vox Humana Chamber Choir for its choral performance. Vox Humana sings an annual concert at the Dominion Astrophysical Observatory in Victoria, under the open roof of the dome, which houses the Plaskett Telescope. Enjoy these 4 beautiful offerings.
Sorry, guys. There doesn't seem to be sound, is there?
thanks very much. Next up, we have a tour of the UVic Observatory with Karun Thanjavur. Let's see. Is Karun's video ready? Ooh. All right, technical difficulties. Can folks hear me all right now? Karun, can you hear me?
Yes, I can.
Excellent. All right. So Karun is part of the Department of Physics and Astronomy at UVic, and he also coordinates the Astronomy Open House, which is an event that happens on Wednesday nights, or at least did during pre-pandemic times, up at the UVic Observatory on the Bob Wright building, where astronomy students welcome the public to their telescope and show them cool things in the sky, answer questions, talk about cool things going on in space. Over to you, Karun.
Thank you, Aaron. Yeah, first of all, thanks so much for all the organizers and especially Laurie to give us these few minutes to talk about the UVic Observatory and some of the work we do here, both regarding teaching and also outreach. And I should apologize, I realize there's a lot of background noise from the big exhaust fans. I'm standing on the roof of what is called the Bob Wright building at the UVic campus. And this is the School of Earth and Ocean Sciences, but there are chemistry labs and they have these big exhaust fans. So I hope you're able to hear me. I'll try to speak as loudly as I can. And I should say it was just absolutely divine to listen to Vox Humana, the singing that beautiful, beautiful lyrics and set to those amazing slides by the RASC members. So thank you for sharing that. I should start off with just saying what an amazing evening it has been. So it's so far enjoyed the presentations, the discussions, all the questions that have been on chat, and I hope this little tour of the UVic Observatory will also be interesting. And I hope we can open up the observatory again, past this COVID pandemic, and invite all of you to come here so that I don't have to do this video presentation, but I can actually show you the telescopes and you can actually get to look through the telescopes. What I'm going to do now is just switch camera so that you can see what I'm pointed at and you don't have to keep looking at my face. So, let's see it. It's like my camera is refusing to switch. There we go, that's much better. So let me just show you what a beautiful evening it is. I'm standing on the roof and we have the spectacular view, and up in the sky, you can see the beautiful crescent. And over here to the west, we are looking towards the Washington State, the Olympic Mountains. So it's an absolutely beautiful setting that we have this observatory. And UVic is one of those very special campuses where we have, in fact, 2 observatories. The one where I am is the more recent one, set up in 2010. But we have a 40-year-old telescope in what we call the Kleiman-Haga Observatory across the parking lot from here on top of the physics building. It has a Lorentz telescope. We've just upgraded all the electronics. We put in a new camera. So we've upgraded that telescope as well, and we hope students will start using it. But most of the work is done here at the DFM, the observatory where I'm standing now. And it's a little bit dark, but off in the distance, you can actually see the Plaskett Dome, the 100-year-old beautiful telescope. So it's a very amazing setting that we have this observatory. So what I'll do is just run through some of the facilities we have here, and then we'll talk a little bit about the programs we offer. So out here on the roof, we have 9 Celestron telescopes, 8-inch telescopes. So these are 20 centimeters. So we use them for near sky, planets, the moon, and binary stars and things that are close by. So most of the time, this is where the open house that we run, the outreach programs, the people come here. All of them have eyepieces, so people can actually look through these telescopes and look at things in the sky. We have a dedicated group of UVic students who talk to the people about what is being observed, give them some background and, make it a really interactive, exciting evening. We also have our own little solar telescope. Doesn't have a camera. What we instead do is project the image onto a little screen. We use this mainly with school groups. Just to talk a little bit about that, our outreach program is very vibrant. I'm talking about the pre-COVID times. We would have on average 2 to 3 school groups per week. Usually, all ages. I've actually had groups from a daycare, the youngest we've had, and of course, all the way to high school and university level students. So it is a very well sought after outreach program that we offer through what is called the Speakers Bureau at UVic. So other than these telescopes, the Celestron telescopes, we also have our pride and joy, the 0.8 meter DFM telescope. I'll actually walk into the dome soon to show you what that telescope looks like. So as I was telling you, the outreach program that we have, we use these telescopes for teaching. So we offer a number of introductory astronomy courses. So all the courses have labs associated with them. So the students get a chance to come and actually use the observatory. We do an introduction to observational astronomy night when it's part of their lab exercise, and they get to look through the telescopes. We talk to them about how telescopes work, talk to them about the objects that they're seeing, and of course, at the end of that, they'll have to write a little lab report just to make sure that they were listening and actually enjoying all this. But other than the teaching component, we also have this outreach program. And as I mentioned, it's very, very popular with the local schools. So on average, 2 to 3 school groups per week, pre-COVID. And I hope come fall, when we're going back to face-to-face instruction, we'll start seeing those groups again. We haven't been able to do any of that over the past year, but we have managed to keep that outreach running with what we call the Wednesday night open house. So it used to be that every Wednesday night, the observatory would be open to the public. It's like a drop-in, runs between 7 to 9 or 8 to 10, depending on the season. And it's been very, very popular, and it's been running for a long time. So again, we have this group of very dedicated, enthusiastic, and knowledgeable group of undergraduates, UVic undergraduates, who do these tours, and they are here to answer questions, show the people things in the sky through these telescopes, and talk to them about those as well. So this is where people come in. So we have a little meeting room. So we may have a little presentation, or this is where the Q&A happens, so that we can project pictures onto the screen. So now I'm just walking up to the dome of the 0.8 meter DFM telescope. So let me just go up. So we haven't actually opened the telescope for the past 15 months, ever since UVic was shut down due to the pandemic in March last year. We haven't used the observatory at all. And I'm really looking forward to reopening this fall. So this is the first time I actually entered the observatory in quite a while. So I've just opened the dome, but we do not have streaming capability here. We have an eyepiece and a CCD, but we don't have any streaming capability. So there's the telescope itself. It's fully automated, so we have a control computer. I just wake up the control computer so that you can see. So it is click and go. So it is run through a software where we can pick objects either directly on the screen or pick objects from catalogs. And there is the control screen itself, the telescope control system through which we can monitor and operate the telescope itself. As I mentioned, we do have a CCD. So recently we have installed a filter wheel, but we haven't actually started experimenting with all these facilities, so I'm hoping come fall, when things open up again, we'll be able to do much more with this telescope. So that is, a quick tour of what UVic has and the programs that we offer. And I'll hand over to Aaron, so that if there are any questions that are addressed to me, I'll be happy to answer.
All right, thank you so much, Karun. Wonderful to see that telescope again. I remember many nights at UVic looking through there and spending long times in the meeting room chatting with visitors and answering questions. And shortly here we'll have a little taste of that with our Ask an Astronomer folks who have been either frequent visitors or other presenters there in the past. But next up, I think we have another quick view of the of some astrophotos from our members. I don't see any questions popping up in the chat or on the Q&A for you, Karun, but thank you very much for the tour.
My pleasure, Aaron. And I should add, Aaron was one of our outstanding volunteer facilitators here for many years. So we do miss you, Aaron. Do come back and visit.
I miss it too. Yeah, once you're doing stuff live again, I'll definitely come down once in a while.
Great. Take care. Have a lovely evening.
You too. Let's see, Randy, do we have time for one question, do you think? Or how are we on the schedule?
Oh,
one just popped up.
A couple minutes late, it doesn't matter. Go for it.
All right, Karun, we have one question for you. Who hires graduates? How does one make a career of astronomy? Yeah, let me find my notepad. I need to get the answer for this one.
So is that directed at me then? Question?
I think so. Yes, it's from Kevin.
Yeah. So yeah, I could talk a little bit about both the undergraduate and the graduate. So at the undergraduate level, astronomy is part of physics. So we pick up a lot of mathematics and physics, which prepares us for specialization in a variety of fields. It need not necessarily be in astronomy, but if someone chooses to continue in astronomy, the usual route would be to go on to grad school, so a master's and a PhD, and then leading into academia, so teaching and research at various universities or research institutions. But the best part is, again, at the graduate level, the training that students receive is so multifaceted, so they become experts in computational work. They're experts to begin with in physics and mathematics. Their writing skills are superb. So they are excellent, if they wish to go into the industry, they are much sought after. And I know several colleagues who have gone into medical physics, for instance, because there is a lot of image processing and similar tools that we learn as part of our graduate program. So overall, there is astronomy is definitely a very specialized field. So the number of jobs available is fairly limited and competitive. But then the preparation that we get as part of our studies kind of opens many other doors, so we are able to go on to other careers as well, if we choose to do that. I hope I answered that question.
I think so, yeah. And I, after my astronomy undergrad, went on to graduate studies in medical physics. So I'm on my track there. Still love astronomy though. All right, thanks so much again, Karun. And
thank you.
I'll pass it over to
evening.
You too, thanks very much. I'll pass it over to Randy.
Well, you're passing it over to me, so I can pass it over to Calvin to do the part 2 of the astrophotography.
Right. Okay. Hop over to Calvin. Oh.
Hey, I'm here. Yeah, I'll just pop on the video here. Oh, this might take just a second. I'm having just a slight issue.
Okay, thanks very much, Calvin. Next up, we have our Ask an Astronomer segment. So I believe we're going to pass it over to Amy here to introduce our Ask an Astronomer team.
Hi again. One of the popular parts of our in-person star parties that we are glad to be able to bring you virtually tonight is our Ask an Astronomer table. We have two experts tonight, Nathan Hellner-Mestelman and Jason Beaman. Nathan says he is a grade 8 nerd. He loves astronomy and loves to share what he knows with other people. He used to volunteer at the DAO with his telescope at our Saturday night star parties. Jason says he is an armchair astrophysicist. He attends the University of Victoria and he loves science outreach. Jason is also co-hosts a science podcast called The Fourth Floor with our own Calvin Schmidt. So as we get started, please type any questions you might have in the Q&A box and we will get them to answer. So first question that I have for you guys is, can the history of solar activity year by year be detected on Earth? Example, by dendrochronology.
Oh, Nathan, you're muted still. I'll take this one while Nathan figures it out. Oh, you're back, Nathan? All right, give her a go.
Oh, sorry. I'm actually unaware of what dendrochronology is. Sorry, Jason, do you think you could take this one?
Yeah. So what they're asking is for the sun's like history is going to leave marks throughout like any kind of fossil evidence or in trees or things like that. And yeah, we can totally measure that kind of activity. There was one of the people that work up at the Hill a lot, Don Moffat, shared a really interesting article. It's the 100-year mark since a solar flare took out most of the electrical infrastructure on Earth. Now, back in 1921, that electrical wasn't much, so it didn't really do it. Everything caught on fire, but that's the worst that's happening. You know, I'm from the interior where things catch fire every year, so it's kind of, we deal with it. But if you're looking, there's a nice little graph there, and you can actually see the sun's like solar activity from the past because they have been able to monitor it for a couple hundred years with telescopes. And yeah, you can go in and measure the effects of increased solar radiation throughout Earth's history.
Awesome. Okay, next question. This one comes from social media, and the question is, are black holes just neutron stars with a much greater mass?
So yeah, I mean, technically you could say a black hole is anything with a much greater mass, incredibly high mass. So usually neutron stars are the last step that anything is before it collapses into a black hole, because neutron stars, they're so dense that the atoms themselves just fall apart into protons and electrons and neutrons, and the force is so great that the electrons and protons get smushed into each other and become neutrally charged, and it all becomes just a sea of neutrons. And at that point, it's so dense that if it were much smaller, it would just collapse into a black hole. So yeah, you could say that black holes are just incredibly dense neutron stars.
Yeah, I mean, and like he says, anything can be. If I were to take the Earth and smush it into something, you know, just like a couple of centimeters in size, it would become a black hole. So it's a couple of factors go into making black holes. But yeah, it's mainly what happens at the very, very end of very large stars.
Okay, next question is it possible for a planet to become tidally locked to its sun or to the sun or to its star?
So yeah, it's definitely possible, and it happens way more often across the universe than in our solar system. We're lucky to have a pretty large, relatively large star in our solar system compared to some other stars. Most stars in the universe are red dwarfs, so they're pretty small. As you make the star smaller, planets usually tend to orbit closer to it. And if they orbit closer, they're more likely to be tidally locked. Now, our star is pretty big and bright compared to red dwarfs, so the planets can orbit, or the planets are not tidally locked in our solar system. thank goodness for us. But around red dwarfs, you'll find a lot of planets that just don't rotate at all around an axis and always point one side towards a star.
Yeah, and actually in our solar system, there is a planet that is almost flukily what seems to be tidally locked, and it's Venus. Venus rotates backwards, and its day is longer than its year, but not by much. So Venus got smacked with something, got really weirdly in a weird rotation, and as it's trying to get out of it, it's going to stop spinning around the sun, and that's going to be tidally locked. Whether or not it stays that way, I have to go read a couple papers on that to make sure, but it's interesting because it's not close to the sun, and it's going to have that same problem from a completely different reason, which is fun. It happens a lot, especially in astronomy.
How long until the Milky Way collides with Andromeda, and how will it look afterwards? And will the Earth be okay?
So the best guesses are that Andromeda is going to collide with the Milky Way in about 4.5 billion years, and it's going to put on quite a show. The night sky is going to look like somebody just like painted it, just like splatter paint with galaxy. The Earth is almost certainly going to be okay. If you look at the density between the stars, one of the most interesting things about that is if the sun were the size of a golf ball, the nearest star, well, of course, it would be the size of a marble, but it would also be 1,600 kilometers away. So there's a lot of space in space. And so the Earth is probably going to be okay, and the stars are just going to like fly straight through the space between each other. And the two galaxies are going to merge into a galaxy, which I think has the most uncreative name of any galaxy ever, called Milkdromeda. It's like Milky Way, Andromeda, Milkdromeda. Creative, super creative.
Actually, it's funny that Venn was here giving a talk because she makes you do the calculation of how often stars will touch when they collide, when galaxies collide, several times. And yeah, this is so big. But the interesting thing about it is that while there's a lot of space between stars relative to the stars, there's not enough space between galaxies relative to the size of galaxies, because galaxies can collide. And it's an interesting like little problem you think of in your head, is that, for some reason, these stars are so small compared to what they live in. But what the galaxies live in is very almost cramped and clustered, and super fun and super interesting.
Okay, next question. Why isn't there an eclipse somewhere on Earth every month?
So yeah, that has to do with the moon's orbit around the Earth being tilted relative to where the sun is. So if the moon's orbit perfectly intersected and was totally flat compared to Earth's orbit around the sun, then yes, the moon's shadow would land on Earth every month, but the moon actually orbits at around a 5-degree angle relative to Earth's orbit around the sun. So most months, the moon either appears to pass either above or below the sun, and it still casts a shadow, but the shadow misses Earth. And yeah, that's why it's only every 6 months or so when those two orbits do align. That's at the point where the moon intersects in its orbit, where, like on the plane where the Earth orbits around the sun. Jason, I don't know if you could explain that a bit clearer.
No, that's perfect. Another thing to also consider, though, is that the moon isn't at the same distance around the Earth in its orbit at all times. And this wobble in that respective orbit, it can actually cause the moon to be in the right spot, but not at the right distance. And so it doesn't quite cover the whole sun. And you end up with like a little sliver of sun around the little sliver of sun around the moon. And it's just because it is weird. And it actually harkens back to the original question, how did the moon form from something hitting? And that was kind of where most of the mass was accumulating was in this weird kind of off angle from the impact. So.
Right. Next question. What is the health of the sun and what changes have occurred over the past century?
The sun is 100 years older.
There's no change. Like we're gonna notice the sunspot cycle, but the sun doesn't care. It's in its main sequence phase, and for a star the size of the sun, that lasts 10 billion-ish years. So it's about halfway through its life in the main sequence phase, and it's just happy as a clam. Like it's getting a little bit brighter. It's like little things are happening, but over 100-year span, in a billion years, it's not measurable really. We notice it because we kind of care, but the sun, it doesn't.
I don't know if any of you have seen the movie Sunshine, but it's definitely not gonna die in 2057.
Okay, next question. Is there an amazing story or similar that the Plaskett Telescope has helped discover?
Well, I know somebody had asked earlier, can the Plaskett be used to find supernova? And actually, a friend of mine has his name on a supernova because he was one of the observers at the Plaskett who happened to point it and find that supernova. So it is still used today for a lot of science. And I'm not quite sure the history of it. Calvin or Aaron would actually be really good and able to answer that question because they live and breathe that place. But I know that, like I say, it still happens today. So.
Right. What is Betelgeuse made of?
Betelgeuse is a red giant or red supergiant star, and it is made of exactly the same stuff as the other stars, including our sun. It has like significantly more matter than stars like our sun because it's so much bigger. But it's the same stuff, star stuff.
Yeah, like Kim had that lovely little image of like the periodic table of elements, and it had the astronomer version. It was hydrogen, helium, and metals. And that's because your hydrogen and helium at like 70-75%, and then your helium's like 20-25%, and then the rest is that little bit in between, and that's pretty standard across all stars. Like when Kim's looking for these metal poor stars, she's not finding things that are super different. Like it's amazing how different they are, but if you were just like looking at it face on, you're like, oh, that's only a couple of decimals different. What's the right? And so it is, stars are almost all the same kind of material. Actually, harken back. Sorry, Dawn just corrected me. Plaskett was used to determine the rotation rate of the Milky Way. That's right. I forgot about that. Thanks, Dawn.
Amy, I think two short or one big question.
Yeah.
Okay, so let's go with feel pressure now. Okay. When we see all the amazing colors in astronomy photos, are these colors really like that if we were in space?
Well, I'm pretty sure if you were in space, you wouldn't see much stuff for long unless you had a spacesuit on. So it depends, because some pictures that are taken like by really cool telescopes like the Hubble Space Telescope, some of them are taken in different wavelengths of light that we can't see. Other ones are taken in visible light, and some of them are also in false color, which I find is kind of annoying, but it does help bring out other details. And so some of them are actually in natural light. And I think there should be like a description. If it's by the Hubble Space Telescope, there'll definitely be a description of the image, and you'll be able to find out what wavelength of light it's taken in.
Yeah, the main issue is A camera is very linear. When you add a photon, it just adds and you just keep adding and adding, and it works great. So you can take color and you can just stare at something longer and do it. Your eye doesn't work that way. First off, it's logarithmic, so you can actually see a dark while you're standing in light. You'll never get that with a phone or a camera. You try to take a picture of a dark spot, you're standing in the light, it's either completely dark or everything's completely light. There is no in between, whereas your eye can really easily tell that difference. But your eye can get away with that because it clicks a picture really quickly. You can't just stack all the photons to see these colors. There's not enough of them. And so as a naked eye, you will never see color in space. It'll always be this little black kind of grayish blue, no matter what you do.
Okay. Randy, I have time for one more. Okay. So I'm gonna, Bella just asked a question. Bella's 10, and she's wondering, are galaxies currently colliding and merging out there? When did the last one happen? Are there photos of any of them happening? What are they like? And what would we see or expect when galaxies collide? I think that's a quick question, Randy. Sorry.
So yeah, they're colliding all the time. And as Jason mentioned, there's a lot less space from galaxy to galaxy relative to galaxy size than there is star to star relative to star size. And so the galaxies are colliding a lot. And you can see that in pictures by galaxies having like these long flung out like galaxy spiral arms. And then two galaxies that are up here close together and that are like connected by these long gas trails. That's a sign that they're colliding. And I mean, there's trillions of galaxies in the observable universe. So there's definitely a lot colliding at this moment. And yeah, it's all really cool because that's going to happen to us in 4.5 billion years.
Yeah.
So
one of the
plenty
more
of ample time to prepare.
Yeah, right? Got all this time. One of the more famous ones that I can think of for a picture is you look up the bullet cluster. This isn't one galaxy colliding, it's a bunch. And it's actually one of the strongest proofs that dark matter exists and exists the way we think it does. So that one's a really good picture of these galaxies that kind of smash together. And you can see, like, if you look at a different picture of the mass, you can see the mass kept going. And to me, it's like, as a theorist who likes that cosmology, it's so good. But yeah, that happens all the time. Our Milky Way, like Kim said, is colliding with in eating galaxies all the time, little guys. So.
Well, thank you, Jason and Nathan. That's the end of the time that we have. So the unanswered questions will be answered in the Q&A box, and I'll enter any of the ones that are on my sheet that aren't there now. So thank you guys so much.
You're welcome. I noticed at the beginning you called me an expert, and if you assume the 10,000 hours thing, if I've logged 500 hours, I'm only 5% the way there. So
you will be there. I know you will be.
If you're using the SI prefix, I've logged 50 milliexperts of experience.
Yeah, even the ones that have logged 10,000 always learn something. That's the key of being an expert.
Yeah.
Thank you so much, everybody. That was just super. I'm going to spotlight you, and we're going to then go to our third of the astrophotography videos. So Calvin, take it away. I think there's been some people saying it's too small, but I think each person watching, at least on Zoom, is able to move stuff aside and try to make it bigger. I don't think there's anything we can.
I'll make an attempt, but I think it's on their end. This might be the best I can do. All right.
Oh
Ooh, ah. Well, I've been watching Erin's video doing some strange things. Now we get to see it. So Erin Bannister and Laurie Roche now are in the center of the Center of the Universe gallery, and they're going to talk about Draco and Hercules.
Yes, hello. So some of you who have visited the center in the past couple of years may have seen some planetarium shows. Unfortunately, we can't do our planetarium right now, but I do have a pretty decent substitute. I have a planetarium in a box, so to speak, a blanket that has all of the stars of the Northern Hemisphere painted and stitched onto it. And I'm going to be using this blanket to tell you a story about some of my favorite constellations here. Let me just charge up so you can see me. There we go. Okay, so we're going to start with a constellation called Draco the Dragon. And you can find this constellation by using the Big Dipper, which is this constellation right here, or part of a larger constellation. And with this, you can follow the first two stars in the cup of the Big Dipper and follow a straight line out to this star here called Thuban, which used to be the North Star. But Thuban is part of Draco the Dragon, which winds its way over the northern part of the sky, sort of around the Little Dipper. Now, this Draco's story starts way back in ancient Greece with the queen of the Greek gods, Hera. Now, Hera had a garden up on Mount Olympus. And this wasn't just any garden. This garden was gorgeous. It grew plants from all over the earth and all throughout its history. The sweetest smelling flowers and the most delicious fruits all found their home here. But the pride and joy of Hera's garden was an apple tree that grew in the very center on a small island in the middle of a small pond. But this was no ordinary apple tree either. This tree grew apples of pure gold. And it was said that if you were to eat one of these apples, you would become a god and live among them on Mount Olympus. And so Hera had many mortal servants, many human servants who tended to her garden. They did the weeding and the watering and planted the tree, and picked the flowers and fruits to go up on the banquet tables of the gods. But she didn't trust any of these servants to get near this golden apple tree. She thought they would try and steal one of the apples and become a god themselves. So she called upon a protector for this tree, none other than Draco the Dragon. And Draco was an amazing guardian. He would wind himself in among the branches of the tree, and he would look out in all directions, never eating, never drinking, never sleeping, never even blinking. And if any of the servants even so much as looked towards this apple tree, Draco would give a snarl so fierce that the servants would go back to whatever it was they were doing. And this went on for many, many months. And every morning, Hera would walk in to the garden first thing in the morning, and she would walk up to the apple tree and she would count to make sure all the apples were still there. Then she would turn around and walk back out of the garden again. Never a, hello, Draco, how are you this fine morning? Or a, thank you for doing such an excellent job guarding my apples, Draco. No, none of that. Just walk in, count the apples, and walk out again. And, you know, after 5 years or so of this, Draco was getting a little tired. He hadn't slept in all those years, too busy guarding. And so he thought to himself, you know, Hera never thanks me for all the work I do. She just comes in and counts. And, you know, after 5 years of being an amazing guardian, I think I deserve a nap. You know, I think he deserves a nap too. And so he looked around and he saw that none of the servants were nearby. And, you know, none of the servants even look this way anymore. I think I deserve, you know, a 5-minute nap. That should be fine. And so Draco, he closed his eyes and he drifted off to sleep, coiled up in the tree. But unfortunately for Draco,
it just so happened that right at that very moment, someone was climbing over the wall into the garden. And this someone was none other than Hercules, the hero. And Hercules had 12 great tasks, 12 great labors he had to do in order to rejoin his father Zeus as a god on Mount Olympus. And the final one of these was to steal a golden apple from this tree. And so Hercules climbed up the wall of the garden, stuck his head over, looked in, and he couldn't believe his luck to see Draco fast asleep. And so he took his chance. He dropped down into the garden, quiet as a mouse, and he tiptoed up to the pond. Then he jumped from rock to rock across the pond, not making a splash. And when he reached the little island, he looked up and he reached and he grabbed the tiniest little apple off the lowest branch of the tree. Then he jumped back from rock to rock, tiptoed to the edge of the garden, climbed over the wall, and was gone. And a few moments later, Draco woke up from his nap. And he thought, oh, that was a good nap, but I'd better go and count all the apples just to make sure. And so he starts counting 1, 2, 3, 4, 5, 6, 7, 8. And he counts all the apples and he comes up one short. So Draco thinks, oh no, okay, I must have been really tired. All right, one more time, just to be sure. 1, 2, 3, 4, 5, 6, 7, and he counts all the apples, and he still comes up one short. Okay, Draco, wake up, wake up. All right, one more time, just to be absolutely certain. 1, 2, 3, 4, 5, 6, 7, 8, and he counts all the apples. Still comes up one short. So he looks around and he thinks, okay, well, none of the servants would have come over here, so let's see. It was a little breezy when I went to sleep. Maybe one of the apples, fell off the tree, and if it fell, it would have rolled into the pond. And oh, hey, there's a little shiny thing in the pond over there. I'm sure that's it. That must be it. Nothing to worry about. I just won't even say anything to Hera when she comes in tomorrow morning, which may not have been the best idea, looking back. So next morning, Hera walks into the garden, and the first thing she does is she goes up to the tree and she counts all the apples. 1, 2, 3, 4, 5, 6, 7. And she comes up one short. And so she puts her hands on her hips and she says, Draco, is there a problem? Draco says, why no, Hera, why? Is something the matter? There's an apple missing from my tree, Draco. Well, yes, but you see, there was a little bit of a breeze that happened and one of the apples rolled into the pond. It's nothing to worry about. None of the servants saw. We're all good. Well, unfortunately for Draco, Hera had heard tell of Hercules' daring exploits, stealing a golden apple right out from under the nose of its sworn protector. And she knew that it couldn't be true, and so she came into the garden to double check. But Draco had lied to her. And she said, Draco, if that had been the truth, that would have been fine. But you lied to me, Draco, and I cannot forgive that. And so to punish Draco, she grabbed him by the tail, yanked him out of the tree, and started smashing him around the garden, left and right, into trees and rocks and shrubberies. And she swung him so hard that her grip slipped. And Draco went tumbling, sailing end over end up into the sky, where he landed among the stars. And that's where he is to this day. And many years later, Hercules was put up into the sky as well, but that's a story for another time. Thank you all very much. And after our next video of astrophotos, we'll be reconvening in the Plaskett Telescope and out on the parking lot to look at some amazing night sky images that aren't on a blanket, they're on a screen.
Too awesome. Okay, Calvin, the exciting conclusion of the astrophotography, and then we'll ask Margie up again.
Thanks very much to all the people who offered photographs and information for our astrophotography and sketch presentation. And it's been a pleasure using the photographs, putting them together, and working with David Lee. We certainly hope you enjoyed the gorgeous photographs and sketches, and thank everyone for their part in the presentation.
Thank you, Margie. That was really, really wonderful. The music and the images, and it feels very good to see our amateur community working together on these sorts of projects. Well, we are going through so many different aspects of astronomy, looking at the work of the professional astronomer, the work of the amateur astronomer. It's a real treat tonight that we've got a clear sky. Oh my goodness, it's super. And so now I'm going to pass the floor over to David Lee, who's going to be leading us on the world of live streaming astronomy. So there's David outside the Plaskett Dome with, well, you introduced the whole team.
Okay, yeah, can everybody hear me? I hope so. Anyways, I'm kind of sooty, but I'm really under a starlit sky. This is
it's a pretty realistic virtual background.
It's unbelievable, actually. There's stars up there. You'll have to take my word for the fact that Mars is right beside the moon. I'll just give you a quick look at the moon right now. So there it is. It's quite beautiful. So this evening we have a lot of things to show you. I want you to know a little bit about the group that's put this together. Dan Posey probably doesn't need any introduction. He's been doing tours of the Plaskett and doing imaging at the Plaskett for quite a number of years. The other people that I will introduce to you slowly is members of a group, a special interest group that we started in January of this year. We call it the Electronically Assisted Astronomy Group. We've been sort of experimenting with this region between visual and astrophotography, which is EAA. So we use all sorts of different types of rigs. Over the season, when we continue with these virtual star parties, you'll get to see more and more of these optical rigs. You're actually looking through one right now, actually. It's sitting right beside me here, and we're actually looking at the moon. But there's much deeper things to look at and deeper sky images to look at. So if we can maybe get some of the people on board here. Dan, are you available? Are you there?
We are here, and we are on Mercury 3.
Excellent, excellent. And is Ruhi, are you there? I see you there.
I'm here.
So Ruhi's from the University of Victoria. She's no stranger to narration. She's a part of the team that actually works on the Astronomy Open House on Wednesday nights, which have gone virtual. And when I saw her do the narration for SLU, I knew she was just the person to do this. So welcome, Ruhi. And
awesome. Thank you.
I see the teams in the control room right now. I get to be outside here in the cold, but I won't say that anymore. Oh yeah, I'm sure it's really warm in there. Yeah. Anyways, I've also got David Payne on the line here. I don't know if you can see Spotlight David here. There's Dave. He's remote. He's somewhat, well, not in the universe remote, but not very far from here. And Dave and I have had some really good chats about EAA. We've been struggling and achieving, and you'll see some of his work tonight. And yeah, I'm really looking forward to seeing that. And we have one more person here. We have Brock Johnson. I don't know if Brock is here. Brock, can you bring Brock online? Maybe Brock's
sure he's here yet.
He's somewhere. Well, I'm sure he'll pop in soon. He's kind of like my ad hoc guy tonight. So I'm going to send him on some potential missions. We've got a list of targets, don't we, Rui?
We sure do.
Yeah.
The first
are you going to lead and just take us through some of the objects?
For sure. Well, if we want to bring it up, the first one that we're looking at right now is M3, which is an absolutely spectacular object. It is actually something called a globular cluster. So these objects are considerably old, some of the oldest objects in our universe. And they are really old stars that are gravitationally bound to each other. So that's why when you're looking at it, it looks like it's a really big circle. So this globular cluster was actually the first Messier object found by Charles Messier, except that he thought it was a nebula without any stars in it. And then, of course, William Herschel came around and corrected it for him and was like, no, this is actually a globular cluster. So just after M13, M3 is actually known as one of the finest globular clusters for observational astronomy. As you can see, it's very bright. It's also like huge. So it's one of the largest, so around like 500,000 stars. And it has an estimated age of about 11.4 billion years old. So again, one of the oldest objects in our universe. They also have, like most globular clusters, this one has the most variable stars for a globular cluster, around 274. And then 133 of those variable stars are actually RR Lyrae stars. So what's special about RR Lyrae stars is that we actually have studied the relationship between the luminosity, so how bright they are, and their period. So they're called like standard candles. So we can actually estimate the distance to anything around them using these stars. So yeah, that's M3 in a nutshell.
Yeah, straight from the Plaskett Dome.
Yeah, beautiful.
Yep. So this is in the control room of the Plaskett Dome. We're viewing straight from the screens that an astronomer would be looking at if they were observing. We get to use the nice giant imaging camera on the side of the Plaskett. And we're going to move along to our next object here. And I thought I'd take you out into the dome. It's the dome proper, so you can see the telescope in its element.
It's not moving as fast
That's
as
a big
before.
Yeah, so it is definitely not as fast as in the video from earlier. Oh, it's actually...
That's a big telescope, Aaron.
Yes. For scale. We are. We'll turn the lights here so we can get our next image. In the meantime, why don't we go over to what David or one of our other EAA folks has on there.
Yeah, do you have something up, David?
No, it's just getting dark enough. I'm just taking the first image, so.
Okay, Brock's just joined us. Brock, do you have anything up?
I potentially could show something. Hold on, let me see if I can share it.
And we're just in readout here, so about another 10 seconds of readout.
Yeah, we'll break to Brock. No pressure.
Yeah. So, screen broadcast. Let's see how this works. So is it going to turn? There we go. So actually what we've got going on here is a live view of NGC 5566, which is a galaxy. Actually, it's a couple of galaxies, one down here and one up here. I've only actually got a couple of frames, I think, so far, 3 stacked frames, but it should slowly over time get clearer and clearer as we get some more frames stacked.
Yeah, so I should mention that's the nature of EAA. It starts off kind of sooty, but that's part of the charm of it. You start seeing little bits and pieces, the brightest spots, obviously. But then over time, it all fills in. So the big difference between this and astrophotography is we don't really try to finish anything. So these things are kind of transient. They're kind of for the moment, and we use them to sort of enhance our viewing.
So the beauty is that you're seeing it develop, and you're getting a quick feedback. So if you're interested in something in particular, you get a question you want to ask the photograph, you're getting your feedback right away, as opposed to conventional astrophotography, which you might wait till the morning to gather all your pictures, or maybe a few nights, and then spend quite a few hours processing them. And you know, if you're an amateur and if you're working, it might be weeks before you actually see the results of your photo of your photography. This way you get an image right away.
And I think we tend to be a little bit more critical about astrophotography. We want to go for the best image. We're not necessarily trying to do that here. I remember the first time I brought up some simple objects using EAA, and I was just amazed by being able to see more than I could see with the eyepiece. And that was good enough. If I wanted to do astrophotography, then I would take the time to do that. But that's not what this is.
The countdown, Brock, is that going to tell us that in 30 seconds, you'll immediately have the next frame in your stack, or is there a delay?
If I was connected with a higher bandwidth connection, but the countdown's the actual imaging, and then there's also the downloading of the images each time it stacks. But I'm running over a very, very slow connection out into my middle of my lawn. So the loading bar at the very bottom there is painfully slow.
Sorry to interrupt, but we're about to grab another image here. So I wanted to show the one we've currently got on the Plaskett screen right now. Randy, can you spotlight us there?
Yeah, that's fine. We can come back to Brock stuff.
Yeah, there we go. So this is M53. It's another globular cluster. Yeah, these globular clusters are, there are a few hundred of them swirling around the Milky Way. Each of them is unique in its own way, but
you have 40 seconds.
40 seconds. All right, each of them is unique in its own way in terms of its age, its metallicity, and to some degree its shape. This one is slightly less round in the core than the previous one we saw, M3. Ruhi may have some additional notes with specifics on its size and age. Ruhi?
Yeah, so this globular cluster is about 60,000 light years away from the galactic center and about 18 kiloparsecs from Earth. What's actually really interesting about this specific globular cluster is most globular clusters have second generation stars. So those are stars that are born from the death of other stars. But this one is actually mostly first generation stars, which is actually very uncommon to find in a globular cluster. I can pull up its age real quick as well.
And just to warn you, you have about 10 seconds before M87 comes on screen.
Okay, cool. The estimated age is about 12.6 gigayears, so very old as well.
Yeah,
I found it. Got
some of the ones Kim is looking at, Dr. Venn.
Exactly.
All right, so
we got the jet.
Oh, fantastic. So this one may be, you may recognize this galaxy from like all the news about anything astronomy over the last year. Oh yeah.
So look up in the corner there, you can see the galactic jet.
So this is M87. It's an elliptical galaxy in the Virgo supercluster, I believe.
Yes.
Yeah. And this one has a supermassive black hole with a very, very strong jet coming out of it. And the black hole at the center of this galaxy is the one that was imaged recently by the Event Horizon Telescope, a network of radio telescopes spanning the globe that looked at this thing for days and days and days, generated petabytes of data, and processed it all to get the highest resolution image of a black hole ever produced. And that image is still generating incredible science now. There was recently the early image of the only direct image of a black hole for sure, and its accretion disk. Now we can only see one of the jets of this galaxy, and that has to do with something called relativistic beaming. Basically, the particles in the jets are moving so fast that any light they emit is funneled in the direction they're already going. So most of the light that comes out of the jet that's going in the opposite direction is funneled along that jet, not back towards us. So we really only get a little bit off the side of the jet that's more or less pointed in our direction. With a deeper image, we would be able to see that jet extending through most of the galaxy. And if you looked at this galaxy in X-ray or radio light, you'd be able to see the jet extending out many times the apparent size of the visual part of the galaxy as well. It's an incredibly powerful galactic jet.
Wow. Well, EA team, should we go home?
No. So why we went to this one first to explain is that we're still fairly early in the evening and it's not very dark for a telescope of this size. So we can only chase very particular bright things at this time of night. And it turns out, we weren't certain, but it turned out that my bet was right and the galactic jet did stand out in quite nice relief. Where normally a lot more of the structure of the elliptical galaxy that is M87 would show through and you wouldn't be able to pick out quite as much detail in the background there. So if you give us a 5-minute reprieve, we're going to do some experimentation and find out a galaxy that we can actually anchor onto and get a good image out of. And we'll turn it over to the EAA group for about five or 6 minutes here.
So how's it going? How's it brewing, Brock?
It's coming along. It doesn't look much different than previously. I interrupted it, and I think the stack didn't load because I flipped to check something on the phone and I interrupted it. But I'm going to give it another 20 seconds here, and it should give an updated view.
All right.
So mine's my second frame. I'm running it like at 6-minute frames. My second frame is almost done. The first one showed a pretty bright background, but I'll let you know when I got a couple of frames. First one was pretty green. Would you like to show what I did last night or not night before last or something?
Yeah, I could do something similar too, actually, after you, Dave.
Sure. No, I have to share my screen here.
Are you going to share, Dave?
Share screen, right?
Yeah. Yeah, you should be able to.
This. Well, that's the final image. This is in Gamma Cygni, which is kind of interesting. I think what I'll do is I'll first show how it was developed in
why is it so red?
EAA. So here's a little bit of a movie. It goes frame by frame as the frames are taken. So you can see, you're playing a little bit with the histogram as you go, but you can see as the frames are taking, the nebulosity in this area, shown in red, starts to come out. You also end up with some satellite trails, of course, as you'd expect, and you're not screening the images before you go, so it's coming out. It's kind of an interesting area. It's just hydrogen-rich area. There's M29, which is an open cluster in the corner here, right near Gamma Cygni star, which is the center star of Cygnus the Swan.
Yeah, it's right. It's right in the middle, isn't it? And I think
Yeah.
I think the Crescent Nebula is nearby as well.
And the star itself, I've got one of the Crescent Nebula in there too, which is one of those Wolfram, can't remember the last name, emitting stars that lights up a crescent of gas around it. But on this one, the Gamma Cygni star is quite bright, and it's just off of the frame, maybe 25 seconds off of the frame.
Okay, thanks, Dave.
I could show what I did the other day with the Markarian's chain.
Yeah, go ahead, Brock.
Hold on.
So you'll notice that some of the people are in their houses. They're actually operating remotely.
So this is the stack as it's sort of starting out early on. I'll just kind of slide ahead a little bit on the time scale. I should have hid some of the menus because it kind of wrecks the view, but this is actually after a number of stacks. This is actually 4 images here. And you can actually see, if I can get this, maybe I'll pause it. But for some reason it's doing this weird darkening at the bottom. But you can actually see Markarian's chain through this region here.
It's
So
a chain of galaxies.
It's a chain of galaxies, exactly. Yeah, they're up in Virgo.
Yeah, the Virgo supercluster.
Virgo supercluster.
That's
So
the home of a
there's-
lot of galaxies, right, Ruby?
Yeah, even the Milky Way is part of the Virgo supercluster.
Ah, cool.
Can I just ask a question? Can
Yeah.
I ask a question about why, is there a reason for those galaxies to be kind of in a curve and an arc like that? Is it part of something that we would see like as an arm of one of our galaxies, that they're kind of gravitationally bound somehow to be in that arc? Or is that just all just like surprise, it's coincidence?
I can maybe speak to that. So for a lot of things in our universe, a lot of it is surprise, it's a coincidence. But these galaxies are actually kind of gravitationally bound to each other, some more than others. So like M86 is one of the galaxies actually in this chain. And this one is actually on the opposite side of the Virgo supercluster from the Milky Way, but is actually coming towards us slowly at 244 kilometers per second. But there's also, I think you can actually see them in there, NG 4438 and NG 4435. They're also known as the EYES galaxies. They're an interacting pair of galaxies. NGC 4435 is a barred galaxy. So if you actually were able to see it, there's a massive bar that goes through the middle of it. And it has a young stellar population due to it actually interacting with its partner. When galaxies interact, you can actually compress a lot of the gas in it. And this causes star formation to actually start up again. And then its partner galaxy, 4438, either gets a lot of its energy from star formation or a possible black hole in the center of it. Astronomers still don't know. They're still kind of trying to figure out. But it has a highly distorted disk with long tidal tails due to the interactions with its partner. And it shows evidence of like modest stellar formation, not as much as its partner as well. There are about maybe 2, 3, 4, 5, 6, 7, 8 galaxies part of this chain. I could go through all of them. I just don't want to, I don't know how much time I have, but.
We're ready over here. We do have a target on screen.
Okay. It's okay. Over to you guys then.
Sure.
So this is the Black Eye galaxy.
Let me unshare.
So this is the Black Eye galaxy, otherwise known as Messier 64. And what you're seeing is really the inner portion of the disk, because there's an outer halo that extends, where did my mouse go? Just out here. You can kind of see the dregs of it, but we're a little bit early in the evening to really pull it out. If anybody's wondering, these dark patches that you see lighting up the screen are dust motes. So we just have a little bit of dust on our sensor. It robs a few percentage roughly of the light that comes in and casts a shadow, which means that we just have to calibrate those out after the fact. And you're seeing the dirtiest, unclean, uncalibrated images you can imagine. So we apologize for that, but that's what you get in real time out of a research telescope. What you're seeing in here is quite a bit of structure. A lot of this is star-forming regions. There's some hydrogen alpha emission that you pick up, which is a very particular wavelength of light let off by hydrogen gas. And in this case, it's let off by clouds of gas and dust. And what's interesting about this one is that it's rotating in two different directions. So the interior portion here is rotating in one direction, and then you have a retrograde rotation on the outer portion as well. But I will turn it over for any more information if I didn't accidentally cover everything.
Yeah, so sort of harking back full circle to Kent's talk, instead of just a couple stars going retrograde or against the normal rotation, we've got a whole extra, a whole chunk of the disk going the opposite direction. Yeah, Ruhi, you got any more information?
I can give you like little tidbits. So basically this galaxy is about 54,000 light years across, so considerably large, and about 17 million light years away. And you can find it in the constellation Coma Berenices. But yeah, you basically covered everything. Good job, guys.
Thank you. It's a team effort. So we'll be getting on to the next target here to hunt down the galaxy. It's taking us about a minute, and then it's 40 seconds for readout. So we'll probably be 3 minutes or so before.
All right.
Okay, I got my image of with two and the third one.
Can we resume?
If you like.
Oh, did you want to finish up first, Brock, or?
Oh, sorry.
No, actually, go ahead, David. I've got another one loading, and it'll be clearer if David does his thing.
Delay. Okay.
Okay. I've lost my screen now. There we go. So share the screen. And I can bring this up. So can everyone see that?
Mm-hmm. Oh.
So that's two images of North American neb, and I should be able to load in another one.
Hey Dave, we see kind of a white haze over it. What's that?
I think that's left over from the first frame.
Oh, okay.
When the sky wasn't really dark enough.
Mm-hmm.
And it's kind of one of the hazards. I think that's what it is. I hope it's not a tree, but it's one of the hazards of not looking at your going through your images. So, you know, as you take more and more images, the bad ones will cancel out. You can see a couple of satellite trails through there as well.
Mm.
Let me go back to the beginning. Okay, that's 3 frames stacked now. And of course, you can play around with the you play around with the color balance, and you play around with the histograms. So that's a little bit more information coming through. It seems a bit red. That's too much. You find with very few images, particularly the color balance is very hard to get right. Sometimes auto generally works the best. But...
Actually, I heard of a function today, Dave, in PixInsight where you can do photometric calibration. So it finds a star by plate solving, and then it matches out all the colors based on the star color.
I've used that, but for EAA, there's lines I won't cross, and opening PixInsight isn't one of them, right? I won't cross that line.
That's against the rules.
And the other thing I'd point out, this is no flats, so there's no calibration, and I kind of argue that one is I'm really not sure. I might change my exposure. So unless I have flats for all my exposures, I could use darks. Maybe that's not crossing the line.
I think that's okay. Actually, it's coming through quite nicely.
Yeah, and the results end up pretty good. So it depends on what you're looking for. If you're looking for something to hang on the wall, it's not going to give you that. But if you're looking to see what something looks like, and if you save the images, there's no reason why you can't process them later.
Yeah, no, I hear you. You know, like sometimes on good nights, I'll just keep my captures and process them later.
Yeah.
So this is the Plaskett image now, David.
All right. I think we want to switch. They want to switch to the Plaskett. So we'll come back. Yeah, go ahead.
Okay. So this, what was this one? This is Messier 88. So this is a spiral galaxy. I didn't actually write down any notes on this one. I just noted that it looked nice and it was bright. What's my main criteria for the evening? So
Dave, you're gonna have to leave your screen.
Oh, sorry.
Oh yeah. There we go. Yeah, so this one is actually coming out super nice. We got a fair bit of contrast in it. This one's another spiral galaxy. This one looks to be all rotating the same direction as most spirals do. It's a grand design spiral, which means that it's one nice disk with with visible like spiral arms, but it's not like a single like a two-armed spiral, which are some of the more common ones. It's about 50 to 60 million light years away. And we're seeing in it, similarly to the Black Eye Galaxy, some lanes of dust and gas where stars are forming. The dust sort of blocks the light from stars inside.
Please. Yeah. So we're now starting our capture on the next galaxy, so we'll have about another minute and a half to talk about this one.
Do you want us to go back to you, Dave?
You got something ready?
Or do you want to go to Brock?
I can show where I'm at.
Yeah, go to Brock.
Okay.
And maybe Ruhi's got something to say.
Oh, okay.
Sorry? Did I get your name?
Which one are we talking about? Oh, no. I was just wondering which one are we talking about.
So this one is still M88, and then to give you the note.
Oh, very nice. That's really coming out now. Very nice.
Okay, cool. So this one's M88. This is still M88, correct? I want to talk about the wrong galaxy.
Mine?
Yes.
This is NGC 5566.
Right. Okay.
Which is a couple galaxies. Well, this is actually the one that's right in the center now. That would be NGC 5566, and the other one, actually, what is the other one that's just above it there? NGC 5560 is the one that's in the center there.
Okay.
And then there's a third one that's off to the side, which I don't know. It's barely visible, but you can kind of see in the center right now is another galaxy that looks like it's kind of colliding with 5566.
Yeah, those
Oh,
definitely look like they're
darks and flats.
interacting.
Yeah, I'll just briefly explain the darks and flats. Those are calibration frames. So they're used to remove the electronic noise, the noisiness. And the flats are designed to remove some of the optical defects. Dan or Aaron mentioned the dust motes. Well, they're removed by the flats.
Awesome. I can say a little bit about NGC 5566, not a whole lot about the other ones right now, but it is a barred spiral galaxy. Again, it has a big bar going through the middle of the center, and it can be found in the constellation Virgo. It's about 65 million light years away from Earth, and it is the biggest in the constellation Virgo, so the biggest galaxy found in Virgo, and it's about 150,000 light years across from tip to tip. Let's see, what else can I tell you about it?
Ruhi, what causes the bar?
That's a great question. So spiral or galaxies in general can form specifically. I'm not exactly sure what causes the bar. Aaron, if you know, that would be wonderful. I can show you the classification though of certain galaxies and what they actually look like.
Yeah, so the as far as I know, the exact formation of bars is still not fully understood. Basically, what you're seeing in the spiral arms of a galaxy are density waves. The arms aren't like stiff in any way. They're just clumps of stars, and stars will move in and out of the bars as they orbit the galaxy. They're clumps in the same way you get clumps in traffic, where like any individual car will move into like a patch of slow moving traffic and then out again, but the patch of traffic still remains. And these density waves are just sort of like instabilities in the disk. Like it would be a perfectly smooth disk, but little instabilities get amplified and form these sort of stellar traffic jams, so to speak. With instabilities that are sort of off center, you can get something like these bar structures in models. I'm not sure if they've fully figured out how they form, but that's the general idea.
Okay. Yeah, you're actually seeing a lot more in the image now, Brock.
Yeah, it's coming along well. Like you actually can make out the bar, and when it's kind of hard, the compression on it's way clearer on my little screen here. But
what exposure is it? You've got a stack of 10 now.
I've got a stack of no, I think it's more than 10 actually.
Oh, okay.
I think it's just that status thing is in the way. I think it might be 16, and they're 120 seconds each.
Okay. Yeah, I found that the 2-minute thing was about right for the kind of stuff that I was doing too.
Yeah, it's enough for like live stacking. Once it's a bit dark, it'd be nice to extend it a bit, but I think it's a decent. After this is over, I'll probably bump it up to 240 and run it for the rest of the night.
You're using a camera too, aren't you? Like a digital SLR?
Yeah, this is with a digital SLR and 1650 millimeter focal length.
Yeah, in future episodes in the virtual star parties in the summer, we'll go into a little bit more detail about some of the gear.
Yeah, it should actually, it's just about to refresh, so it might get slightly better. See if it gets any clearer.
We're ready to go with M91 over here.
Okay, perfect.
Right.
I will stop my share.
Good time to transition.
Okay. Yeah, so this one is not quite as nice as the last one. We're still working against some fairly light skies for our telescope. It likes it good and dark, but you're seeing the central bar of this galaxy. And Ruhi, you want to take it from there?
For sure. Again, it's a barred spiral, also found in the Virgo supercluster. It's about 63 million light years away. And what's kind of special about this galaxy is astronomers actually called it an anemic galaxy. So it's a spiral galaxy with a small amount of star formation and gas. So that's not normal for spirals. Spirals and irregular galaxies are known for heavy star formation. And this guy isn't doing much of anything in that aspect. It is also, 63 million light years away. Let's see. I think that's all I got for this one.
Is that can you de-Bayer that? Is that a Bayer matrix I'm seeing?
No, you're seeing the screen of the monitor itself.
Those are screen pixels, Dave.
Yeah.
Oh, okay.
Yeah. We can't we can't stream directly from this computer screen due to NRC's IT security, but we can take an image of it with the phone. I mean, it's nice, you know, when the moon hits your eye like a big, or there's a version of it that talks about the moire pattern. What is it? Oh gosh, I'll have to look it up. But, it's the XKCD comic.
Oh.
Okay.
Anyway, I don't remember it either. That's all I did.
When a grid misaligned with the grid that's behind, that's a moire.
I love it.
Actually, Aaron, if you just twist it a little bit, the moire might disappear.
Oh, that's not too bad there.
Yeah.
Yeah, so we're only just seeing like the barest hints of the outer arms there, just because the sky's still quite bright. But we're on our way to our next image, so we'll have that shortly if we want to pop over to an EAA scope.
So Dave, do you have anything for us?
I've got a couple of things for you. I want to show you another quick movie and then an update on the North American galaxy.
Okay.
So here was M51. This was taken a couple of weeks ago. You see how rough, but you still get a pretty good image. And the images are stacking and playing around with.
Are you sharing, Dave?
Dave, I'm not sharing, am I? Oh.
Described it so well. It seemed like it was there.
That video player was working so hard.
Yeah.
There we go.
So you could see, I mean, a lot of the flashing is me trying to adjust the histogram and get the color balance right and the right brightness as these images are taken. This is with a longer focal length than the other one. This one's 2,500 millimeter focal length. And you know, you get the satellite trails again, but you still get a lot of detail. You can see other.
Oh, you got a little galaxy there.
Galaxies, but down there and one there. So it's interesting and it's a lot of fun at the same time doing these things.
Ruhi, what can you tell us about M51?
Oh my God, so much. So this is also known as the Whirlpool Galaxy. So they're two interacting galaxies. So NGC 5194 is interacting with NGC 5195. So basically a big spiral is interacting with a smaller dwarf galaxy. So it's about 31 million light years away from us. It has an apparent magnitude about 8.4. So if you use binoculars on like a dark sky, you'd actually be able to see this. So the main spiral has H2 star forming regions in the spiral arms. So if there, you see like the kind of reddish areas in the spiral arms, that's where stars are actually being born right now. It's also 43% the size of the Milky Way galaxy, so about half the size of ours, and about 10.3% of the mass of the Milky Way galaxy. So considerably smaller in mass, but almost the same size. And it has an active galactic nucleus at the center. So that basically means it has a black hole at the center. And star formation is happening at the center of M51 as well, although it's not sustainable. So star formation at the center of this galaxy will probably end within the next 100 million years. What's really interesting that I actually just found out when I was Googling this galaxy is that the first extragalactic exoplanet candidate, if confirmed, is actually found in the Whirlpool Galaxy.
Wow.
So it was found through eclipses of an X-ray source, so either a neutron star or a black hole, and a massive B supergiant star. So if confirmed, they think that the planet would be slightly smaller than Saturn in our own solar system. And then a little bit about the dwarf galaxy. So it's been interacting with M51 for hundreds of millions of years, and that's made this dwarf galaxy highly irregular. You can see there's not really a shape to it. It's kind of everywhere. And then the interaction has also caused the compression of hydrogen gas in the dwarf galaxy, also causing star formation. So these galaxies will eventually merge as well.
Have they already passed through, or they're about to pass through?
They've had a couple passes already, and eventually these guys will merge after a few more passes.
Mm.
Yeah.
Interesting.
So here's 4 images. Just going to add another one.
Okay, we're ready when you are for another Plaskett one.
Yeah, we're going to wind this one down in a couple of seconds, Aaron.
Okay.
Go. Liking that.
We're waiting for a stack, Dave? Or?
Yeah, there we go. Added the next one. Didn't see much of a change. But typically for this, for this type of target, I would probably go to bed and stack the about 40 images in the morning.
Okay. Okay, we better move on back to the Plaskett. There's like 10 minutes to go before they have to before they get evicted. Okay, go Plaskett.
Yeah, so this is Messier 65. It's one of the members of the Leo triplet. What you're looking at is a bit of an in-between. It's not quite edge on, but you're seeing the dust lanes along the side of the galaxy going, where's my mouse? Up and down here. And then you're getting some of the spiral characteristics, as well as the very typical popped out core, just because it's a bit bright. You're capturing all of that dynamic range in one frame. I will pass it over for more detail, just because I don't have notes on hand for this one.
I've got a few things. So this galaxy is low in dust and gas, which means that there's little to no star formation actually happening in this one. And the ratio of old stars compared to new stars is quite high. So this galaxy is on the verge of dying unless something sparks it up again with some more star formation. So they also, I don't know if you can kind of see it from this image, but from other images, the disk of M65 is slightly warped, and its relatively recent burst of star formation is also suggestive of some external disturbance. So Wikipedia is telling me that there is a little bit of star formation in the arms, but it is slowly dying, which is kind of sad. But
so did something take the hydrogen away or something like that? Or?
Yeah, so they do think that M65 interacted with something about 800 million years ago. Doesn't tell me anything about what it might have interacted with, but there was definitely something that crashed into it.
Plus 42 degrees,
yeah.
30 seconds.
It's a little hard to see, but I don't know how well people can see the very top of the image, but the spiral disk like tilts just a little bit at the edge there. It tilts this way, a little bit at this edge. So that's the warp in the disk, I believe, that Ruhi's referring to.
So Ruby, we're just slewing to Messier 63, which is the sunflower. And then at that point, we'll have a choice between Messier 106, or we might be able to try for Messier 51, but it's right on the limit for what I can get to tonight.
Yeah, we're coming up to 10:53, so I guess we'll have to make some choices, I guess.
We may just have time for this one more, depending.
Yeah, why don't we come back to you? Okay, for EAA people, how do we want to finish up? Do you have something to show us, Brock, or?
I could give you the latest here, yeah.
Okay.
It's slowly getting nicer.
that's the final image from the Plaskett, so we're going to pass it over from there. We've just hit a dome stop, so we have to do a bit of TLC on this one.
Well, thank you very much, Plaskett.
Yeah.
Excellent.
Yeah, it's getting clearer. The bar feature is definitely showing up, and the neighboring small galaxy that's interacting with it is showing up better.
Mm-hmm. Well, that's actually a lot better than it was.
Yeah, it's pretty good.
So Brock, you're operating off of a tiny little Raspberry Pi device on your telescope.
Yes, which is talking to my iPhone. So yeah, it's the Raspberry Pi is doing the stacking and then sending me images.
Very nice.
Makes it quite easy.
May I ask a question then? Are you, is your Raspberry Pi actually using a camera that's plugged into it, or is it just doing the stacking, the actual computation?
There's a DSLR, Canon DSLR, plugged into the Raspberry Pi, and the Raspberry Pi is taking the images from the DSLR and then doing the stacking on it.
Which is attached to an SCT, a 9.25-inch SCT.
Yeah.
Yeah, I don't know if the audience has any questions for us. We're probably almost ready to go off the air. Randy, what do you think? Are we going to stick around for a little while, or are you going to give us the hook?
Well, what's left now is huge thank you to this David. You've been preparing for this day for weeks. I'm so impressed. This is my first time getting to see images forming live in front of my eyes, and I'm really quite excited to see where this technology goes.
Yeah, I share your excitement. Yes.
Yeah, it has been a lot of fun. We barely scratched the surface. And I want to thank the Plaskett team as well. I know they have to really struggle with where they can go. And also, as the summer progresses, we're going to have less and less darkness. So I think you'll probably find that the EA group will bring stuff that they've recorded in the wee hours of the morning and bring them pre-recorded.
Well, it's amazing you get so many images in such a, like the light gathering power of that thing must be just massive.
The Plaskett is
phenomenal.
Yeah, like the time I just pointed at it and it looks like 10 hours of integration on my scope.
Yeah, that's unfair.
Yeah.
So I just wanted to pop in as well and say a huge thank you to everyone who's helped out with this event tonight, especially Lori for organizing this whole thing and wrangling, herding all of us cats to get all this together.
Yeah, thanks, Lori.
Yeah, thank you.
To our solar crew, Sid, Chris and David, our EIA crew, Brock, David, and Ruki. Many thanks to Kim Venn, our speaker for this evening. Thanks to Randy for emceeing with me tonight.
Thank you, Aaron, for doing it with me.
Thanks. And as well, Dan and Ben over in the Plaskett. This is the first evening we've actually been able to get live streaming working from the Plaskett Telescope. So hopefully that'll be a feature of our start parties to come over the summer, as well as more EAA. Oh, Calvin, yes, Calvin, and Amy for putting together all the behind the scenes tech stuff here, making sure all of this actually works for us. Jason and Nathan, our Q&A crew, our Asking Astronomers. Yes, it was wonderful hearing you. I can't wait to hang out with all of you at Wednesday night open house again in the after times. And once again, thanks to everyone and have a fantastic night.
Thanks,
if you're watching
guys.
us on YouTube, please like and subscribe. That'll help us get these out to more people in the future. Also keep an eye on our Facebook, Instagram, pretty much anywhere you can find us at Friends DAO. Follow our posts there to get notified of more events like this in the future. Have a good night. Clear skies, everyone.
We're also thanking Karun Thenjavar of
yes, Karun.
UVic.
Right.
Beautiful
Yes, yes.
tour of the UVic Observatory. We have very rich in the astronomy community in Victoria. We are very well endowed, and it's very it's just a joy working together.
We hesitate to say, don't forget to smash that like button, share and subscribe, because that sounds a little bit enforcing. So we could say, just, we encourage you to.
Yeah.
Just
Please help us out.
Just press that button.
Yeah.
Yeah. Gently caress it. All right. Have a good night.
Good night.
Good night, everybody.
Good night.
Good night.